Good morning, everyone. So the session is from now on recording and broadcast live on YouTube.
I always wanted to be on YouTube.
Okay, so we're starting in a few seconds. So welcome everyone to the last day of the power sessions. Today we have a set of really nice heavy ion talks, which mostly focus on a bulk medium properties. So we're going to have 6 talks before coffee break, and then also 6 talks after the coffee break. So the first talk is going to be by Manuel Lawrence, and he's going to explore the QCD phase diagram in the region of highest mu B with Hades. So Manuel, you can start sharing your slides.
Mm-hmm. So you can see my slides and you can hear me?
Yes, please start.
Very good. So I'm going to speak about, as said, about exploring the high mu B region with Hades. So let's have a look at the high mu B region. Here you see a sketch or a visualization of a central gold-gold collisions at square root of S of 2.4 GeV at 3 time steps, before the first collisions, then after 16 Fermi over C, and then at a rather late stage. Can you see my hand, by the way? Oh, okay.
Yes, yes.
Yeah, okay, very good. So, and what you see here is the density profile. And what you also see is that the interpenetration times at these low energies is rather long. So the spectator matter stays rather long in the collision zone. So there's no clear separation between the fireball and the spectator region like we have at higher energies. And what you also see is that most of the matter is stopped really in the collision zone. So the baryons are staying in the collision zone. This is why this is baryon dominated matter and why we have high mu B. And if we look at the beta versus polarity plot, which we use for particle identification, which you see on the right here, you can already get a feeling for the system which is created in these collisions. First of all, you see that we have much more particles on the right than on the left. So we're dominated by particles over antiparticles. There are basically no antiparticles there, or no antibaryons there. And then the second thing you see is that we are dominated by baryons over mesons. So if we look at the yield per collision of these hadrons, we find a very clear hierarchy. We have about 100 protons per event. About 50 more protons are bound in light nuclei, which means that at these energies, light nuclei are not a rare probe, but really make up the bulk also of the matter. Then the only abundantly produced meson are the pions. We have about 10 pions per event. Then 10 to minus 2K plus per event and 10 to minus 4K minus. So basically everything else than light nuclei, protons, neutrons, and pions is rare, and strangeness is especially rare. If we compare this evolution, which I showed you on the left of the heavy ion collision, to merging neutron stars, you find some similarities in the density and also in the temperature profile. See, this you see in the lower plot. Of course, there are also differences. They don't hit bang on, but they circle around each other before they start to merge. but the density and temperature profile is rather similar, which is rather cool because then we can really probe the matter or create the matter we have in merging neutron stars also in the laboratory with similar properties. Yeah, and if you then do this, let's come to the HIME-V side. If you then do to the yields, which we measure in this experiment, fit with a statistical hadronization model, you end up at baryochemical potentials around 800 and temperatures below 70 MeV, which you can see here. So we are really at the very right side of this diagram. Okay, here's a short outline what I'm going to present today in the talk. I will focus on gold-gold collisions at square root of S of 2.4 GeV. We've analyzed 2.2 times to 10 to the 9 events. So we really collected a lot of statistics. And I will show that, of course, the statistics is important for the rare probes like virtual photons or strangeness because they are so rare. But I will also highlight how this helps with bulk properties where you can do then more differential analysis. So as I said, first I'm going to focus on virtual photons. Here we have this very strong couplings to the baryons because there are so much baryons around. And then here's the famous diagram of the rho meson, which is modified in nuclear matter by this coupling to the baryons. Secondly, I will focus on subthreshold strangeness production. This is very interesting because it's produced below the free NN threshold. And therefore the energy to produce strangeness has to be in some way provided by the system, which is created. And you also see that there's a substantial difference in the thresholds between K plus and K minus. So this leads to a kinematical suppression of direct K minus. And similar like the rho, the K minus is expected to couple strongly to the baryons. You can draw similar diagrams, which is shown here, or you can have a strangeness exchange reaction for this. So of course, this K minus you cannot measure in dilepton channel. You have to rely more on indirect measurements if you want to see the medium properties. So these two observables I will use to address the aspects of medium emission or medium modification. And then I will come to bulk properties, which I said is basically protons like nuclei and pions. Here I will address proton number fluctuations, where we have a paper out this year, flow anisotropies, and pion intensity ferrometry. This I will use more to characterize the bulk of the matter and the collision itself. At the very end of the talk, I will give then an outlook to the future, which is called Phase Fair Zero, Fair Phase Zero. And I will try to convince you that this is not just a nice marketing name, but there's really some meaning behind it because we use detector technology, which is, for example, developed for fair experiments like CBM already in HADES now. Okay, in case you haven't seen HADES, here are some pictures of HADES. You see here's a more schematic view. It's a fixed target setup, and you can see the subdetectors in measuring position. Everything is shrink together to 3 meters. You also see a photo at the end of the setup. It looks like this. And currently it's located here. See a photo of the GSI fair complex. Currently HADES is located here on the left in this experimental hall. And then in future it will be moved for this fair project to this similar or this CBM HADES cave. And what is here, this picture is taken by a drone flight from April this year. So nice thing, what you see in fair, there's really something happening. So they're really building since a few years now the infrastructure there. Okay, let's go into the data, and I'd like to start with virtual photons. Here you see already the spectra we measured in gold-gold collisions at 2.4 GeV. You see black and red dots. These are two different analysis methods which nicely agree with each other. And what you also see is a line of the freeze-out components, the long-living components at freeze-out. And in blue, an elementary reference which we collected in proton and neutron proton collisions. And what you find is that for the invariant mass region above the pi0, you see a large excess above this elementary reference. So we really see some contribution from the medium. And to investigate this medium contribution further, we isolated this excess by subtracting the NN reference. And then you get the following picture. This is shown here. So you see now this is basically the radiation which comes from the medium. And you see, first of all, it's more or less structureless, which means that we see a strong broadening of the row due to this direct baryon row scattering. And we have an exponentially falling spectrum. So we can use Boltzmann fits to extract the temperature, the source temperature of this. And if you do so, you get a temperature of about 72 MeV of this, integrated, of course, over the whole evolution of the collision. You can also compare this to transport models or models which use the coarse-grained approach, which means you have a transport model running to do the evolution of the complete system. And then you do an addition based on the medium spectral function radiation of the row meson, like it's done at SPS, RIC, and also at LHC by, for example, Rapp and company. And you see two versions of this. One is from the Frankfurt group. This is this line here. And then there's also three versions actually. Meanwhile, also SMASH is doing coarse-grained approach. And then there's this GSI Texas where Ralf Rapp is involved. And you see that especially at a high invariant mass, this spectra is rather good described. So this means really that this baryon-driven medium effects, you can cook a consistent picture all the way from cis energies up to over SPS and RIC up to LHC energies. What is also interesting, we investigated this, this excess as a function of the system size. This is shown in the lower plot here. You see a ratio to the elementary reference, basically. And what you see is that for carbon-carbon, you see basically no medium radiation. But as soon as you go to argon KCl, you see an onset of this, this excess or this medium radiation. And then in gold-gold, it's about a factor 6. So it's really that similar to this observations of the Na61 that at some point you might call this maybe also onset of the firewall. Okay, moving on, going now to strangeness, which is related to this. And I'd like to start with a reminder. There's a long story at these energies that the K- freeze out later than, compared to the K+, because they couple to baryons and you have strangeness exchange reaction. Actually, there was one experiment at GSI called the chaos experiment in the 90s, which did a lot of this. And they claimed that the K- production is coupled by strangeness exchange to the K+ production, and therefore they come out later. However, what at that time was not measured is the phi to K- ratio, and this is shown here on the left. You see it's rather constant at high energies, and it stays constant all the way to LHC. In the picture of the thermal model, you can explain this by this limiting temperature. So temperature stays constant for this, the ratio stays constant. But if you go to low energies, this ratio increases. And this means that about, if you take the branching ratio into account, about 25% of all K- come from a phi decay. And this effect is not negligible on the spectra, so you actually have to correct the K- spectra for this feed down from the phi decays. Note that for the K+, you can neglect, the effect is only a few percent because we have 2 orders of magnitude more K+ at these energies than K-. So the effect is only important for the K- spectra. However, you see these are so rare, 10 to -4, so we don't have so much statistics. The green dots here are the data. So we did instead, we tested the hypothesis whether we can explain the spectra of the K- with the same, that it has initially the same slope like the K+, and then just the feed down of the phi comes on top, and that makes it to seem colder compared to the K+. And if you do so, you can find this the green line that you perfectly can describe the K- spectra. So the takeaway message is if you take the feed down of the phi meson into account, there's no indication from the K- spectra for sequential K+, K- freeze out, which is quite important. But we went one step further. We looked at the complete strangeness production in gold-gold collisions at 2.4 GeV. And as I said in the introduction, this is a really nice, unique observable because it's all the hadron production thresholds are higher. So you have to go to 2.55 GeV or 2.86 GeV to directly produce strangeness. So if you look at this system, so the energy must be provided from the system. And here you see now a plot which summarizes this. You see the multiplicity as divided by our part as function of our part. So we look at the centrality dependence of the yields. And you find that all the yields, like the lambda, K plus, K0, K minus, and also the phi rise with the same increase as a function of a part. And this is rather surprising because you would expect from the different thresholds here that the K minus and the phi meson have a stronger rise with a part because you need more energy. And for this, the more collisions you have or the more particles you have in the system, the more likely you have to gain enough energy. However, this is not the case. So we really observe here in universal a part dependence, and this points to the fact that the hierarchy in production threshold, well, I said, is not reflected, and it rather looks like the scaling is here. It scales with the absolute amount of strangeness and not with the individual hadron states here. So it means probably the system is first deciding that strangeness is produced, and then only at a later stage looks how it redistributes this to the final hadrons. Okay. Moving on now to bulk properties. We have a paper out on proton number fluctuation this year. So it's the first analysis at these low energies. And it's really a very detailed study of experimental effects. So it's a rather long paper, more than 30 pages. I listed here the contents of the paper. So if you're interested, here's the reference and you can go there and to dig out all the investigations we did, because of course this is a very demanding observable, and we did a lot of systematic checks to get a feeling for the systematic uncertainties we have on this measurement. Meanwhile, I think it's accepted by the journal and should be out also in the journal version this week or next week. Coming to the comparison to higher energies. Of course, everybody is waiting to compare this data to the results obtained from STAR. STAR was doing their analysis in a rapidity window of plus minus 0.5 units in rapidity, all the way from 200 down to 7.7 GeV. The problem with this rapidity window at hardest is that, first of all, you don't have a clear separation anymore, as I said, between the spectator and the fireball matter. And then also the acceptance of, this is at the edge of the acceptance of hardest. So we choose two variations. One is the, so to say, the maximum safe acceptance of hardest. This is rapidity plus minus 0.4. This is the lower picture here. And then also the one where we really think that we are safe from the spectator effect. So this is mid rapidity plus minus 0.2. And you can see the trend compared to STAR. Actually, I think in STAR, this is only statistical errors. In hardest, there's also systematical errors included. And the uncertainty due to this variation in rapidity, you can also guess from these plots. And in addition, in the paper, there's also a plot showing you nicely how this changes with changing the coverage and rapidity. But what you see basically is there's room for some interesting structures. Okay. Another way to look at these data without the energy dependence is to look at the NP scaling of the correlators. So the cumulants Kn, they hold information on multi-particle correlators. So if you look at this, you can isolate some relevant physics. So on the left, you see the C2 as function of a mean number of protons, then C3 and C4. And what you find is that that they scale with a power of alpha. This goes to n basically. So here you have basically 2, 3, and 4, which is a signature for long-range correlations. So somehow we observe in our data hints for long-range correlations. And one thing one could guess is that this is due to proximity of the liquid-gas phase transition, which is close by at these energies. Okay, I have to move on and come to flow anisotropies. Just a reminder, I said in the beginning, we have long interpenetration time. So the passing time is at the same order of magnitude as the expansion time of the fireball. And for this, we have squeeze out because the matter is blocked by the emission in the reaction plane by the spectator matter. This leads to this sign change in V2. And all the results are reconstructed with, based on the event plane method, with a forward wall detector, which is measuring the spectators in the forward wall in the forward region. Here are the data. You see proton, deuteron, triton, V1 to V6. Here are the odd and here are the even harmonics. And this is really the first analysis in this energy regime up to V6. you see, yeah, and this is really where also statistics, of course, helps, because we can go up to V6, which never was done before. And if you've done so, you can also do a parameterization of the Y dependence and then do some more nice visualization, some 3D visualization of the particle flow, which you see here. And what you find basically is that at mid rapidity, we see an almost elliptical shape. The odd coefficients are consistent with 0. And then if you go to forward, backward rapidities, you get an additional triangular shape. Could be that this is due to an interplay between the central fireball pressure and the direction with the spectator matter. Moving on, we can also look at the scaling behavior. So ideal fluid predicts this 0.5 for the scaling of V4 over V2. And this is shown here on this plot. So you see for protons, neutrons, and tritons, and mid rapidity, this perfect or this ideal fluid prediction is almost reached. So that's also quite interesting. However, interpretation of these energies is not straightforward. Moving on to identical pion intensity ferrometry. So we had this paper out last year. So we are the first to really observe this. There were some indications before, but we really see substantial difference in the charge sign of this pion correlations. And if you look at the trend with energy, you find that the hardest data, if you look at this R side or R long, or the volume in total, seems to follow more the trend from star Na49 than from E895, which goes rather high up here. So there could be room for structures. But we also went one step further and did this pion correlations as function of the event plane angle in 5 bins. So a bit more differential. And then from this, you can extract the eccentricity of the collision. And what we find is that the initial nuclear overlap eccentricity is relaxed at freeze out. So we get more or less a picture of the evolution of this 2 pion source. Okay, coming at the end to fair phase 0. We had a very successful beam time at under this scope of fair phase 0 last year in March. You see here we were running with 16 kilohertz. We collected about 16 billion events, and black is what we recorded as function of beam time. Green is what we anticipated. So we really got what we came for. And as I said in the introduction already, this is not just a fancy name, this fair phase 0, but we use really detector technology developed for fair detectors. In this case, for example, parts of the CBM rich photon detector. With this, we improve our ring detection in the Cherenkov detector, which we use for E plus E minus. And here you see already now the efficiency corrected dielectron spectra from silver-silver. We took this at 2 energies, this higher energy 2.6, and then at lower energies in order to be able to compare to gold collisions, which I was speaking of most of the time. In addition, we also have now a new ECAL detector which measures neutral particles or photons. So we can reconstruct pi 0. You see the peak there. And we also, just to give you a feeling for the quality of the data, we also do, of course, strangeness. And you see here K0 and lambda spectra all the way from backward rapidity over mid rapidity to forward rapidity. And it shows you, gives you a feeling for the data quality. And some Easter egg here. What's really nice, we also look at the hypertriton, which is not that straightforward at these energies. There might be a peak somewhere at slightly higher energies of this rate, but at cis18, the rates are supposed to go down. And here you see a hint for a signal of a hypertriton. So this would also be the first measurement at around mid rapidity, which at these energies. Okay, we have a very rich program for the next years to come at cis18 before we move to cis100. If you're interested, we just handed in several proposals for the period from 21 to 25. But I think I'm running out of time, so I go to the summary. I showed you virtual photon production, and we see this temperature. We can extract this temperature because it's really a very exponentially falling spectrum we observe. And then we see this onset of this radiation in I1KCl collisions. In strangeness, I showed you that there's no indication for the sequential K plus K minus freeze out if you do the proper correction for the 5 feet down. And we observe this universal apart dependence. And then in the bulk, I showed you some proton number fluctuations, flow anisotropies, and pion intensity interferometry. And I showed you that also here, statistics help to really go very multi-differential or up to very high orders. And fair phase zero, high quality data not to come, but is already here, and a lot to come in the next years. And this is the team. And thank you very much for your attention.
Thanks a lot, Manuel, for very interesting talk and really nice HADES results. So we are open for discussion. We have a couple of minutes. Reminder to participants, please raise your hand if you would like to ask a question to Manuel. I'm going to check the Mattermost channel. So in case you would like to discuss more, there you are, of course, welcome. So let's wait for a bit for any question. Okay, I think your talk was really clear. We have a lot of results to digest.
Yeah.
But I think it's really great to see those lower energy results, and now we can try to look at this a bit more systematically when we have this. I see one hand from Yuri. Yeah, that's what I expected. Okay, so you can go ahead, Yuri.
Yeah, that's a comment which so simply a comment about the scaling behavior from hydro for the V4 over V2. So I guess, I mean, as you rightfully noted, there are a few caveats. So I would say that it's rather a nice coincidence that the V4 over V2 is kind of almost at the level of 0.5.
Yeah, I mean, I said interpretation is not straightforward, and I think what Barbara said, you have to go now to do this more systematically. I mean, see how the scaling behavior develops as function of energy. I mean, if it's just a coincidence, then you expect that you don't see reasonable energy dependence, so to say.
Okay, thank you. So again, I invite people to discuss on Mattermost later, but I think we have to move to the next talk. So thanks again, Emmanuel, for a really great talk. Now we move to Jakub Zimmermann. Jakub, could you please start sharing your slides?
Yeah.
Okay, I can see you.
Okay, so now it should be full screen.
Yes, you can go ahead.
Okay, so good morning. I have today the great opportunity to talk to you about my recent research together with Christopher Plumberg and Boris Tomashik about the shape of the correlation function. The correlation femtoscopy is nowadays a standard technique for the experimental analysis of heavy ion collisions. The two particle correlation functions are usually fitted by Gaussian. However, it seems that the real shape is not Gaussian. This shape is better reproduced by Levy stable distribution, and it has been suggested that the Levy shape with specific exponent may identify the critical point. However, we check if the low value of the Levy index can be caused also by some non-critical phenomena. I'll start with some basic definition of the correlation function. It is defined as a ratio of two particle spectrum and the product of two one-particle spectra. And it can be computed according this second equation. Here, K is the average momentum of the pair of particles, and Q is the difference between the moment of the two particles. We use this special outside long coordinate system, where the long coordinate or longitudinal coordinate is the same as the beam direction. The out coordinate is defined as the transverse component of the K vector, and the side is then perpendicular to both of the directions. As I said, usually The correlation function is parameterized using the Gaussian parameterization, where the R's are the well-known HBT radii or correlation radii, which gives us the sizes of the homogeneity region. Now we parameterize the same correlation function using Levy parameterizations, which is given here, where R's are very similar to the HBT radii, but they are not exactly the same. Here, the alpha is what we call the Levy index. And it is obvious that when we set alpha equal to 2, we obtain Gauss distributions. When we set alpha equal to 1, we obtain exponential distributions. So the lower the value of alpha index is, the Levy index is, the farther from Gaussian distribution the function is. The third equation here is one-dimensional Levy parameterizations, where Q will be defined in next slide. So we focused on 4 main effects which could cause non-Gaussianities. The first one is ensemble averaging. We know that each event is different, has different sizes, has different anisotropies. But to increase statistics, we have to average over many events, and that can affect the shape. Another way to increase statistic is one-dimensional projection. So we calculate correlation function not as a function of three-dimensional vector, but as a function of scalar quantity. And here we assume 2 options for this scalar quantity. First one is Lorentz invariant Q, where it is equal to minus Q mu, and then longitudinally boost invariant Q, which is given by this longer equation. Then there is K averaging. Since we use bins, we cannot take these bins arbitrarily small, and thus we have to average again over some pair momentum interval. The last but not least are resonance decays because Gaussians are given by one scale, but different resonances contribute with different length scales and different time scales. Thus, the correlation function must deviate from a Gaussian form. Let's now move on to the models we used. First, we used last wave model. It is a theoretical model characterized by the emission function, which is Wigner density. Here, the red factor is called Cooper-Fiber factor, which gives us the flow of the particles through the fiber hypersurface. Then there is Gaussian smearing in proper time, Boltzmann thermal distribution, transverse box profile. The E star is energy in the local rest frame. R bar is dimensionless transverse coordinate, and eta is space-time rapidity, and tau is longitudinal proper time. Blast wave model has also 2 types of anisotropies. The first one is spatial anisotropy, which means that the shape of the fireball is not circular, but for example, as in the figure, it has elliptic or it can has also triangle shape, and it is given via this equation where an are the spatial anisotropy coefficients, theta is angular angle, and theta n is event plane angle. Then we have flow anisotropy, which describes the transverse rapidity via a Fourier series. And it means that the flow is higher into some directions, for example, in this figure to the right and to the left, while it is the flow is lower to the up and down in this figure. Here, rho m is the flow anisotropy coefficient, and theta b is angle perpendicular to the fireball surface. To actually generate events, we used Dragon, which is Monte Carlo event generator based on blast wave. It has also added resonance decays. For this study, we generated 50,000 events with parameters set that temperature is equal to 120 MeV, fiber radius equal to 7 Fermi, freeze out the proper time is equal to 10 Fermi over C, rho 0 0.8, and the parameters of the anisotropies A2 and rho 2 are fluctuating between minus 0.1 and 0.1. To generate correlation functions, we used Crab, Witten-Bryce-Scott Pratt. To find out if our results are not just some issue of the model, we calculated the same things with the second model, and we used the IEB Vishnu, which is 2+1 dimensional hydrodynamic simulation with Israel-Stewart viscous hydrodynamics and with Glauber Monte Carlo initial conditions. From these events, we calculated HBT using hot coffee, which calculates event-by-event correlations functions directly from Cooper-Frye integrals, which means no hadron phase or hadron cascades, and it also includes all resonances. For this study, we generated 1,000 0% gold-gold collisions at 200 GeV, temperatures again 120 MeV, the eta over S is 0.08. So first, we start with the one-dimensional correlation function because it is done more often because of the statistics. So we started with the hydrodynamical approach, and we compared three of the effects. First, thermal versus full, which means the thermal pions without resonances versus full pions with resonances. It is difference between left and right figure. All figures, we show the Levy index as a function of KT. So left figure is thermal pions, while on the right figure there is full pions with resonances. We can see that while the value of the thermal pions is about 1.5 to 1.9, the full have values from 1.2 to 1.7 or 8, which means that the Levy index actually decreases with resonances. Then there is a comparison between single event and event averaged. That is the difference between blue and green lines and red and light blue lines. Then there is a comparison between the definition of the scalar quantity Q, and that's between blue and red versus green and light blue lines. From these figures, you can see that the influence to the shape of the correlation function is not as strong as the influence of the resonances. Then we studied event-by-event fluctuations. So we generated events with averaged over the spatial anisotropy coefficient, A2. So the coefficient was fluctuating between these values, and averaged events, which means we set fixed value of the A2. You can see from the sketch how the A2 could be, how the shape was averaged. But the effect is not as strong. We did the same with the flow anisotropies. And again, you can see from the sketch, it's not visible very good, but this means that the flow is higher in in horizontal direction. Here is higher in vertical direction. But again, the influence of this averaging is not very visible. The last is the effect of the fluctuation of the event plane direction, and this is also not very strong effect. So now I move to resonances. So again, here you can see the results of blast wave, which are the points not connected with the lines, and the hydrodynamic results, which are points connected with lines, and the difference between resonances and without resonances. The resonances are given by squares, while thermal pions are given by circles. You can see that for both models independently, the resonances push down the value of the Levy index by 0.2. Let's now move to three-dimensional correlation functions, but I start with one-dimensional fits in each direction separately. So you can see the left figure results for blast wave model, and on the right figure the results for hydrodynamic model. The different colors gives us different directions. Blue is for X direction, red is for Y direction, and green is for Z direction. Full lines and points means events with resonances, and empty points and dashed lines means events without resonance. From this figure, you can see that the directions X and Y, that means the blue and red points and lines, are affected more than resonances than the green lines and points. That means that the transverse directions are more affected by the resonances than the longitudinal direction. To better understand what does this mean, we generated profiles of the emission sources. So we took pions from KT interval 300 to 400 MeV, and we plotted the sources in each direction. And we can see that the longitudinal direction is much wider than the transverse directions. That means that the value of the Levy index must differ for each direction separately. The last fit is the three-dimensional Levy fit to three-dimensional correlation function. Here again, the full points are blast wave model. Empty points means hydrodynamic model. Blue points and lines means thermal pions. That means without resonances, while green points and lines are with resonances. Again, we can see the effect of the resonances, which is strong, extremely strong for lower KT, while a little weaker for the higher KT. To better understand the results, we calculated also the corrections to higher order. So we decomposed the data into Levy expansions up to first order. Here, L1 is Levy polynomial, in this equation, and C1 is a complex Levy coefficient. We found that such fits are very unstable, but we got some results. Here is the results for a three-dimensional Levy fit to three-dimensional Levy through three-dimensional correlation function for a blast wave model. And here is actually the result of the coefficient C1, which gives us how strong the correction is. And we found that actually the first order corrections are not negligible. That means that our correlation functions are neither Levy shape. This brings me to conclusions that the index of the Levy stable parameterizations fitted to the correlation function may be influenced by a variety of different mechanisms. In our results, it deviates substantially from the value of 2. We found from all the effects that 2 effects gives the most significant deviations from the value of 2. The first is projection from three-dimensional relative momentum to scalar Q. The second most significant effect is resonance decays. As we use two different models for the calculations, we can say that the conclusions are robust against different models. That's all from me. Thanks for your attention.
Thank you, Jakub. Very interesting study. So now we have some time for questions. Thanks for staying on time. So let's wait. So please raise your hand in case you have a question. I'm going to check if there's something from the Mattermost. We don't. Yeah, there's a raised hand. Please go ahead.
Yeah, hi, Jakub. So thanks for the interesting results. One result caught my attention, that's slide 13, when you show the 3D correlation functions from hydro and blast wave.
You mean this one?
This one, yes, exactly. So actually what is interesting is that, so X, Y, Z are outside and non-direction. Is it correct? Sorry, the sound was jumped. I didn't hear.
Yes, X, Y, Z means outside long.
Okay. So then basically what is interesting is that the Z direction in hydro for the thermal pions seems to be still away from Gaussian. So that's different from blast wave. So essentially I was wondering whether it's understood why the blast wave and hydro results are different in this sense for the thermal pions in the Z direction. I mean, both of them are boost invariant calculations, I suppose. And so I cannot really imagine why the green dashed curve is going down at low KT. But okay, that's rather comment.
Okay, thanks. In case you can discuss further on the Mattermost results. Okay, don't see more hands. Maybe we have one more minute. Maybe from the experimental side, I can ask Jakub. So from your studies, is there any suggestion you could give to the experiment in terms of these fittings?
So the main conclusion is that this work was motivated by the low values of the Levy index, which were measured by the Phoenix. The conclusion of this work is that you have to check also some of the non-critics before someone concludes that they found, for example, critical value of the Levy index.
Okay, thanks a lot. Let me check again the chat. There's nothing in the chat. Okay, so I think we will move to the next talk then. Okay, thanks again, Jakub. And now we move to the next talk on femtoscopy by Andreas Matis. Andreas?
Good morning.
Morning. You can start sharing your slides, and Andreas will talk about characterizing the particle emitting source using femtoscopy in PP collisions with ALICE. Please start.
Yeah, good morning, or whatever the clock tells you in your local time zone. So I'm very happy to present here today results on how we can use femtoscopy to characterize the particle emitting source, in particular in small collision systems. Now, such collision systems have recently attracted quite some attention. And the reason for that is that there are striking similarities between small collision systems, such as proton-proton on the one hand, and large collision systems, such as proton-lead. And just to illustrate this to you, I want to just briefly flash an ELISE result on strangeness enhancement. Now, strangeness enhancement, of course, is considered as one of the key signatures of the deconfined phase of quarks and gluons. And what you see here is now the ratio of yields of different particle species containing strangeness normalized to that of pions as a function of the charge particle multiplicity. And basically the key message of this plot is, first of all, that there's a smooth evolution from the small system to the large one regarding the strangeness enhancement. But even more interestingly is that high multiplicity proton-proton collision show basically a similar degree of enhancement than central lead-lead collision. And that is, of course, a very interesting question in itself. And the question to ask is, of course, what is the origin for this effect? And now in our studies, we use a complementary tool to study such effects. And what we use is femtoscopy. This has already been introduced in the previous talk. And the general idea here is that we study correlations in the relative momentum distribution of a particle pair. And of course, what happens if there is an attractive interaction among two particles emitted close by from a source is that they will attract one another and shift the whole distribution to smaller relative momenta, allowing us to observe an enhancement. So experimentally, what we do is that we just measure the relative momentum distribution in the same event, and we normalize it by an uncorrelated sample, which is obtained by using event mixing techniques. Now, from a theoretical point of view, the beauty of this approach is that this allows us to assess the integral of, first of all, the emission source, which basically steers the interparticle distance upon emission, and the two-particle wave function, which of course incorporates the final state interaction that is responsible for the reshuffling of the momenta. And now traditionally, this method has been used extensively with pairs of known interactions, so where the two-particle wave function is known, and here in particular, of course, pion-pion and can pairs have been used. And this method has been used, of course, then to assess the emission source. And what is very nice for us for this approach is that it allows us to assess the collective behavior. And the reason for that becomes very clear by realizing that these correlations only appear for small relative momenta. So if we now just look at a finite volume from which random emission of particle pairs occurs, so for instance, just a thermal bath, you immediately see that the particle pairs with low relative momenta can be formed from all over the volume. And indeed, the resulting femtoscopic radii therefore reflect the full size of the volume. Now, on the other hand, if there's a collective emission of particles stemming from flow effects, the picture changes because, of course, the particles are all boosted outwards, and pairs with small relative momenta can only be formed in a confined part of the reaction volume, and accordingly, the measured radii will shrink accordingly, and therefore, with femtoscopy, we measure the so-called length of homogeneity. And of course, what one has to realize is that this length of homogeneity shrinks the more the particles are boosted. And indeed, this is something that we have found in data. So what you see here are now results from lead-lead collisions, where you see the one-dimensional femtoscopic radius as a function of the transverse mass, which basically reflects the average transverse momenta of the particles. And we see a couple of interesting things in this plot. So first of all, you can see that the centrality dependence of the radii, just look at the first bin, reflects very trivially the simple geometric picture of the collision as the geometric overlap of the two colliding nuclei. So the radii increase with centrality. But even more importantly, and relating to what I just said before, the radii shrink as a function of transverse mass. So this reflects a collective behavior. And if this so-called MT scaling now were perfect, so all particles would line up on the same line, this would mean that there's a simultaneous freeze out and a common velocity boost. But if you take a closer look to this in the most central collisions, you can see that here in particular, the pions stick out. So the scaling is broken for pions. And while there are now different interpretations nowadays of this effect, there's no clear picture of what is going on. And as we've already heard in the last talk, here strongly decaying resonances play an important role. But of course, the role of these resonances is even more important when going to a smaller collision system. Now, if we look at a similar picture in proton-proton collisions, here again, the femtoscopic radius as a function of the transverse mass, the picture is a bit different. So still, there is some kind of multiplicity dependence going from small to larger multiplicities, which of course is now a bit more difficult to interpret and probably related to a superposition of individual sources. But there is also a slight MT scaling, but it is, of course, not at all common. So if you compare the charged pions to the charged kaons in the same multiplicity bin, you see that this is completely broken. So there's no common scaling at all. But again, we have to realize that the source distribution is modified by strongly decaying resonances. And of course, in small systems where the radius is only of the order of 1 Fermi, and thus comparable to the C tau of such typical resonances, a comparison among different particle pairs is only valid when these resonances are properly accounted for. And of course, you can also see that here in the small collision systems, indeed the measurements are focused at rather low transverse mass. So what we want to do is, first of all, we want to understand the effect of strongly decaying resonances. And secondly, we would like to extend the MT range of the measurement. And this we do by choosing baryon-baryon pairs in high multiplicity proton-proton collisions. And we have developed a formalism to account for the resonances. And this is something that we have put on the archive. Now, let's first take a look at the measured correlation functions in a given MT bin. And we have chosen to look at proton-proton and proton-lambda pairs. And for the proton-proton correlation function, you can very nicely see the interplay of the different involved interactions, where you see the attractive strong interaction and then repulsing hitting in from Coulomb and quantum statistics. Now, on the other hand, for the proton-lambda interaction, there is only a strong attractive interaction, which is of course also well reflected in the correlation function. And now to conduct these fits, we have first of all started with a pure Gaussian-shaped source, and we have computed the theoretical correlation function with our in-house developed CATS framework, which allows us to solve the Schrödinger equation. And of course, for proton-proton pairs, we have used all relevant interactions, including the Argonne V18 model for the strong interaction. On the other hand, for proton-lambda pairs, the interaction is far less well known than for proton-proton pairs. So we use employ chiral effective field theory at leading order and at next to leading order. But you can see in both cases, the femtoscopic fit yields a more than reasonable description of the data. So if we now study the resulting Gaussian radii as a function of MT, we first of all see very very nicely that the radii scale with MT. So they decrease with MT, which now, coming back to what I said in the beginning, in large collision systems, this is interpreted as the pattern of a collective evolution of the system. But you also see that there is a significant offset between the radii obtained from proton-proton and the radii obtained from proton-lambda correlations. So of course, the relevant question here to ask is, first of all, are these two particle pairs emitted from a different source? Or can it be that this is just the effect of strongly decaying resonances, which leads to an artifact in our measurement? And to answer this question, we have developed the universal source model, which indeed is the first quantitative approach to model and correct for the effect of strong resonances. So the general idea of the model is that it features a Gaussian core from which all particles are emitted. So not only the particles of the pair of interest that are emitted from this core, but also the resonances that feed to this particle pair. And then on top of this Gaussian core, we add an exponential tail, which incorporates the strongly decaying resonances. And this part has basically two ingredients. So first of all, we of course need the relevant resonance yields, which are here obtained from the statistical hadronization model. And you can see that for both the proton and the lambda, the primordial fraction, so the particles produced in the primordial collision, is only about 1/3, while the remainder stems from strongly decaying resonances. And then of course, we also need the decay kinematics, and these are obtained from EPOS. And of course, the most interesting question in the following is, how does the inclusion of strongly decaying resonances affect our source shape? And here you see the probability density function of the resulting source. And first of all, I want to highlight the Gaussian core we start with this, which is here depicted by the black dashed line. And then if we add on top of this core the resonances that feed to the proton-proton pair, you can see that we start to introduce quite some exponential tail in the distribution. But, and this is actually some good news, if we now parameterize this with an effective Gaussian, the description holds actually very well up to about 6 Fermi, but of course the resulting effective radius is slightly larger with respect to the core that we started with. For the proton-lambda pairs, this effect is even more enhanced simply because the lifetimes of the resonances that decay to a lambda are much larger, and this is well reflected in the distribution, where you see that the exponential tail is significantly enhanced. And also here, the Gaussian parameterization holds well up to about 6 Fermi, but again, the effective radius is now even more decreased. So we see that starting from the same core source, the effective radii for proton-proton and for proton-lambda pairs significantly differ. And this is basically what we saw before. And indeed, if we now correct for the effect of these strong resonance decays and only look at the core radii obtained from the femtoscopic fits, you can see that the MT scaling prevails, but also that the radii of proton-proton and of proton-lambda pairs are common. So of course, now the question is it only, does this only hold for proton-proton and proton-lambda pairs, or indeed is the source from which the particles are emitted universal for all pairs? And for this reason, we employ our formalism to the most commonly used particle pairs in femtoscopy, namely charged pions, which allows us also to significantly enhance the reach towards lower MT. So for charged pion femtoscopy, we have obtained preliminary results in minimum bias proton-proton collisions. And indeed, there is one further experimental challenge related to the pions, namely the fact that in small systems, there are abundantly produced from hard fragmentations, which we call so-called mini-jets. And this leads to an autocorrelated background in the correlation function, which is simply not present for barium-barium pairs. And in order to remove part of this background, we use event selection criteria, namely the sphericity, which is obtained from the eigenvalues of the transverse momentum matrix. And indeed, as it turns out, this observable is correlated with the number of hard parton-parton scattering and allows us to reject pencil-like jet events that also contain such mini jets, and instead allows us to select spherical events in which such structures are suppressed and thermal production dominates. And indeed, we have analyzed the charge pi correlation function in a number of multiplicity and KT bins. And in order to further suppress the residual mini-jet background, we employ Pythia simulation, which, as you can see here, overall describe the background rather well. However, some discrepancies remain, and this will be accounted for in our femtoscopic fit. Now, of course, before going further, we again need to talk about the ingredients to our universal source model. Now, of course, the Gaussian core is still the same, but since we're dealing with pions, we of course expect the exponential tail from strongly decaying resonances to be significantly different. And here this has been evaluated from thermal fist computations. And indeed, while the prime audio fraction is still about the same, so still roughly 1/3, the composition of the resonances is now significantly different. So it's shifted towards larger C taus. And here in particular, there is a sizable fraction which has a C tau larger than 5 Fermi, and which in our model is assumed as a flat contribution to the correlation function. And then also what we should realize is that since now we are dealing with mesons, they're significantly lighter than baryons, so the decay kinematics will also be significantly altered with respect to what we saw before. And this is, again, well reflected in the resulting source distribution. So here again, the probability density function of our source. And here we start with a core radius of a Gaussian core radius of 1.5 Fermi. And if we add on top of this all the resonances, you can see that this red distribution differs significantly from a Gaussian shape. And indeed, it is rather well described by an exponential distribution. This is something that we have also seen in the previous talk and is also expected and in line with recent studies at the LHC and at RIC. Now, for our model correlation function used for the fit, we fix the lambda parameters from single particle properties, so they are not free for the fit to determine. Indeed, basically all ingredients of the fit, so the resonance contributions, the lambda parameters are fixed, and then the charged pi signal is again modeled using our in-house developed CATs with quantum statistics and the Coulomb interaction as input. And as you can see, with a polynomial of second order to account for the residual background from mini jets, this yields a very good description of the data. Now, I said before, there is still some remainder of the mini-jet background, which here is parameterized with a polynomial of second order. To be conservative, we also employ a polynomial of first order, however, at the expense that this significantly deteriorates the chi-square. So let's take a look at the results. So here you see, again, the core radius as a function of the MT in a low multiplicity bin and in a high multiplicity bin. And you can see that we show the results for the polynomial of first order and second order baseline separately, but the overall trend is consistent. So again, first of all, we see, as expected, that the core source increases with multiplicity, but even more interesting, that at large MT, the scaling does show up. And now, of course, the most relevant question of this talk, is it now a common scaling? And unfortunately, this answer is not straightforward to answer, because first of all, the pi-and-pi results are in minimum bias. The baryon results in high multiplicity. But if we select a comparable multiplicity bin, we see that the largest MT bin of the pions suits very well in the overall trend of the baryons. So indeed, it appears that there's a common emission source, but of course, for the moment, take it with a grain of salt. Further studies are underway to solidify our results. And with this, I'm already at the end. So I showed you that with the first quantitative treatment of short-lived resonances, that we can treat them with the universal source model, and by correcting for the effect of these resonances, we find a common emission source of proton-proton and proton-lambda pairs, and also the pi-and-pi results fit in very well. Now, of course, this MT scaling that we have observed is in large collision systems interpreted as the pattern of a collective behavior. And of course, this is now something that needs to be further understood why we observe this also in small collision systems. So we have here a complementary approach to study such effects. This is, of course, very exciting in itself, but it is also very important for us to have a good knowledge about the particle source, because it allows for us to revert the idea of femtoscopy to run detailed studies of the interaction among particles, in particular hyperons. And for this, I would refer you to the talk by Oton on Wednesday. And thank you very much for your attention.
Thank you for the nice talk. So now we have some time still for questions. I see Boris raised hand. Boris, please go ahead.
Yes, hello, thank you. I like this very much. And I remembered some time ago, Mike Lisa and Zbigniew Chajęcki were doing, I think, very similar things for STAR. They were also looking at proton-proton collisions, as far as I remember. And the big issue for them was the momentum conservation, because that had an influence on the correlation functions, or somehow, as I remembered. Does that play a role here, or your multiplicities are high enough that you don't have to worry, or do you have to worry about that? How does it work?
I mean, this is something that we see in our data, and this is something that shows up at rather large K-star. The low K-star region is indeed almost free from such effects. So to the percent level, we see in Monte Carlo a perfectly flat baseline, and also in the data, there are no artifacts in the region that we study, that we're interested in, that point to a large contamination from such effects.
Okay, thank you. I guess, Boris, you're fine with the answer. And
yeah.
Okay, thanks. And we have one more question. So, Yuri.
Yeah, okay. So thanks. Those are wonderful results. I actually have a rather comment to this empty scaling, which you show on slide 9, or rather to say the absence of the empty scaling. I mean, there is probably some confusion about that. So the empty scaling is only achievable. I mean, there is an exact result derived in a model without transverse flow. So if you have 0 transverse flow, then you'll have empty scaling. Otherwise, the empty scaling is basically broken by the presence of the transverse flow. So if you, I mean, I would be rather surprised that you see empty scaling rather than you don't see it. So in the sense, the empty scaling is I mean, it's not a signature of the collective transverse expansion at all. I just wanted this fact to be clear.
No, it's clear. I mean, in particular, by looking at one-dimensional radii, this is much more complicated, of course. but still, depending on the models you look at, there is still some remainder of this scaling in the behavior of the radii, right? But thanks for the comment.
Okay, thank you. I think we have to move on, but anyway, you can discuss this further on the Mattermost channel. I don't see more hands, so thanks a lot, Andras, again. Now we move to the next talk, which is from Yushen Shen. Okay, yes, I can see your slides. If you wish, you can share your video as well.
Okay.
Yeah.
Can you see my slide and
yes.
hear my voice?
Yes, Yushen Shen will talk about the search for long-range flow-like correlations in hadronic E+ E- collisions with Belle. Please go ahead.
Yes, so we are glad to have this opportunity to report the measurement of the two-particle correlation in hadronic E+ E- collisions on behalf of the Belle collaborations. The two-particle correlation functions have been long established in the heavy ion fields, and with one of its main purpose to probe the collective and isotropic charged particle behavior out of the quark-gluon plasma mediums. And in 2005 to 2010, Rick has launched the first measurements in this kind of series using the gold-gold collisions. And here just show the Fobo results. They get a very dominant near side peak correlations, meaning that the charged particle pair basically having the eta and phi coordinates very close to each other. And eta here is the pseudo-rapidity, phi here is the azimuthal angle. And this is widely regarded as the intrajet correlation. And besides these features, they also observe very novel structures, which is termed as the rich signal. And the rich signal means that the charged particle pairs are depart largely in the eta directions, but they have very similar phi coordinates. And since LHC has conducted this kind of search with different collision systems, like the lead-lead collision, the proton-lead collisions, and also the smaller system like the proton-proton collisions. And they also find this kind of very interesting rich structure. But till now, the origin of the rich signal is still not clear. And there are several possible theoretic candidates to account for this, like the hydrodynamic flow that follow the initial state fluctuations, or the color gluon condensate effect. And there are still numerous of other mechanisms that can account for this. So years ago, our teams are quite interesting in this kind of issue. So they conduct experiments, they conduct the measurement in a very elementary collision system, say the E+ E- collision systems using the LF archive data. And what they turn out is that they don't see a rich enhancement in this kind of two-particle correlation function search. And we're also very curious about what we will get in the very clean system and very low energy at the Belle experiment. So this is the first measurement of the two-particle correlation function at the B factory energy scale. And in this energy scale, the dominant events are typically the E+ E- annihilation to the QQ bar fragmentation. And the advantage of this search is that such kind of clean environment provided by the E+ E- system don't have the complication of the initial hadron structure. So the result can be complementary to understand the origin of the rich signal. And we also compare our results from data with different simulation models. So we believe this this comparison can be the new input into some tuning of the simulation. And we also conduct the analysis with a different construction of method, say the thrust coordinate axis. And we propose that this method is more sensitive to the soft emissions. So here I introduce the data set we use is the hadronics E plus E minus annihilation data collected by Bell detectors. And we only utilize a fraction of data that is the intergrade luminosity is 31.5 inverse femtobarms. And below show the landscape of the KK accelerators and also the side view of illustration of the Bell detectors. And we have asymmetric E plus E minus being here. So in terms of calculation of the two particle correlation, we will boost all of the particle firstly into the center of mass frame. And we would like to first give you some sense of what Bell data look like. So here, since we are calculating the charged particle angular correlations, so here we show the distribution, the multiplicity distribution of the charged particles. And compare with numerous of previous two particle correlation experiments, we can see that the charge multiplicity for Bell data set is very low. And thanks to the Bell statistics, we are able to find result in a very stringent multiplicity bin configurations that with a charge multiplicity greater or equal to 14, that's only make up of 0.02% of the Bell full event. And here, let me briefly talk about the two particle correlation function observable constructions. So the terminology, the signal correlation functions, meaning that we will take one trigger particles and pair it with another particles to count the angular difference. And we will count into all the contribution of one event, the pair acceptance, to make the signal correlation functions. And in this kind of constructions, we will unavoidably get the effect of random pairing effect. So this is why there will be another background correlation functions that count totally irrelevant charge pairs. So with these two correlation functions, we can do the factorizations and also multiply by a normalization to get the final two particle correlation function observables. And we can also do a more specific check in the specific range. And since we are more care about the long range, so we can integrate over the long range interval. And in our analysis configuration, the long range definition is 1.5 to 3. And we can do the projection onto one dimension to see the associated yield as a function of delta phi. So let's look at the result of the Bell two particle correlation function in the low multiplicity regions, which having the offline multiplicity between 6 to 10. And here it is the two-dimensional correlation functions, and below show the one-dimensional projections to the delta phi dependence. And we also superimpose the Bell official PCI-based Monte Carlo on the data point. And we can see the agreement is reasonable between data and the Monte Carlo. And we would like to look into different region of the correlation function that measure in the Bell sample. So we have a mild near-side correlation function, near-side correlations. And this is typically the intrajet correlation that's having the charge particle pair very close to each other. And there are also a structure elongated at the away side. And the away side means the delta phi is roughly equal to pi. And it is typically the this kind of back-to-back jet topologies. So the charged particle pairs will reside in the in the digest event, and they can pick up opposite phi directions. But the jet orientations can be rather arbitrary. So that is why there will be a elongated structure along the delta eta directions. And we also like to look into that whether there are rich signal in the Bell E plus E minus data. So we are like to look at the shaded regions in this two-dimensional or one-dimensional regions. And we can see that there are basically no enhancement, there are no bump pop out here. So basically we don't see the rich enhancement in the Bell data set. Also for the high multiplicity event, the observations are quite similar, and the magnitude of the correlation function is greater than the low multiplicity region. And we would like to, the second part, we would like to talk about another construction of the analysis, say the thrust, using the thrust axis coordinate. And we will firstly like to talk about how do we calculate the event thrust. So in the calculation of event thrust, we will take into account the charged particles, the neutrals, and also the missing momentum we regard it as a particles. And the thrust algorithm is conceptually to choose directions that can maximize the inner product between the directions and the other particles' momenta. And the thrust value is the sum of the inner products. So we can get some sense in this result based on the lab data. So the event with the low thrust value means that the events are more spherical. And when the thrust value approaches to 1, we will get a more digest or pencil-like event topology. And on the right-hand side, we show the thrust distribution of the Bell data set. It is very different from what we see in the lab data, although both are the E plus E minus collisions. But with a very different energy scale, we can see that in the Bell data sets, the thrust value are generally smaller, and also the distribution are wider. And here we also superimpose the PCI-based Bell Monte Carlo with the data point. And we can see the agreement is generally good between the data and Monte Carlo. And here we'd like to talk about the innovative construction of the calculate of the correlation function in view of the thrust axis coordinate. So here we will choose the thrust axis to be the newly defined z-axis in replace of the original beam axis. And after since the charged particle pairs now their kinematics variables, say the PT eta phi, will be recalculated based on this newly defined z-axis, the thrust axis. And we would like to motivate a bit why we want to do this search using different coordinates. So the correlation function is more sensitive to the transverse mid rapidity regions. And in view of the beam axis analysis, it is the region where the hydrodynamic effect of the anisotropic collective charged particles can be detected in these correlation functions. And this can be some hint to the QGP mediums. And in view of the thrust axis analysis, typically in the E plus to E minus, E plus E minus to QQ bar fragmentation events, the transverse region will be the soft emission of possible gluon jet, and also, if any, we can find the quark-gluon plasma state. And one would like to ask why the correlation function is more sensitive to the transverse region, but not the forward or backward regions. So here we show that in the correlation function look like this, digest correlation with one particle set at the forward region and another set at the backward regions. They can have a very large eta difference. And basically, since the two particle correlation will have a finite delta eta range, so it is basically out of our interest. And the second contribution will be the interjet correlation with jets set in a forward or in a backward of the coordinate. And when viewed this correlation globally, you will think that the two tracks are very close to each other. But in view of this coordinate with the reference z-axis stepped into the two, the tracks can take up an arbitrary phi coordinate. And in this instance shown here, we can see it is roughly opposite phi coordinate. And here we show an interesting demonstration of this kind of correlation in view of different coordinate analysis. So the leading interjet correlation in view of the beam axis coordinate, we can get a very prominent near side peak since they are very close to each other. But when viewing in the thrust axis coordinate, the jet is basically will be sit on the thrust axis. So this kind of effect will be, we will observe some kind of effects that dilute along the delta phi. So the correlation now is diluted away. So with this understanding, we would like to look at the interesting results in our thrust axis coordinate. This is the results shown with a low multiplicity event. And here we also do this data Monte Carlo comparison, and we see there are some discrepancy between data and Monte Carlo. And for the high multiplicity event, we see similar trends with a low multiplicity event. And the interesting things to observe is that there is no interjet correlations seen in the thrust axis coordinate. So recall what I say, the sensitive region of the thrust axis coordinate constructions is where the soft emission will happens. So basically in the Bell collision energy, the soft emission is too soft to form a very prominent near side peak as other experiment. So we also do an interesting demonstration that's tune the collision energy from all the way from the Bell data configuration to 50 GeV with the Sherpa simulation. And this is what we get. The Sherpa simulation at the Bell data configuration are really resemble to the Bell data, and there is no near side peak. But when the collision energy increase, we can see the near side peak also evolve. And this is a more detailed view in view of the one-dimensional projections with this short range. We can see this is also evolved as a function of the collision energies. And we would like to look at whether there is ridge enhancement at the thrust axis coordinate. Basically, we see the correlation is quite flat and there is no bump also. So we would like to quantify the ridge signal as other experiment and using the conventional ZYAM method. And by integrating over the ridge prone region, we can get the ridge signal. But basically, we don't observe the ridge signal in both coordinates. So we will decide to set the upper limit using the bootstrap method. And this is what we get for the beam axis and thrust axis analysis. For beam axis, we set a strong exclusion of not observing the ridge signal. For the thrust axis, we also see there are no ridge signal visibly. So we have the 5 sigma exclusion and also the 95% upper limit. We also compare the data with the predictions from the other event generator with the Herwig and Sherpa. And on the top, it is the multiplicity bin configurations with 12 to 14. And on the bottom, it is the highest multiplicity bin. And on the left, we firstly see under bin coordinates, in the near side ridge prone region, all of the generators are actually in quite good agreement with data. But when viewed in the thrust axis coordinate, the Herwig prediction seems to fail to describe the data. And we find that the PVIA is the best to describe the data. And finally, it's just the conclusion of this analysis. So we performed the first measurement of two-particle correlation with Bell data. And the interesting things we found is that in the thrust axis construction, we see there's no prominent intrajet correlation at the origin. And since there are no rich signal in both beam and thrust, so we will give the upper limit of not observing this kind of correlation. And we also do comparison with different generators. And the conclusion that we remark is PVIA is basically give us the best description on the data. And this comparison can be the new input to the simulation generator. And we are also interested with the search on the Upsong for S resonance in the B factories. And this part of analysis is also ongoing. So we are very expect to see that. Thanks for your listening.
Thank you, Shen, for very nice talk and perfect timing. So now we have time for questions. Okay. So please raise your hand if you have question. I will check if there's something from the Mattermost channel. I see discussion, but no questions. Yeah, there's one. Okay, go ahead.
Yeah, very nice results, actually. Very interesting. Thank you. There is one, maybe not such a serious question of actually looking at the particle multiplicities and essentially answering the question whether the multiplicities of different hadrons follow this statistical hadronization model case. So that's...
You mean, please go ahead if you still want to.
Basically more of a coarse observable, basically yields of different hadrons, and whether the yields fit the statistical hadronization model.
So can I take it as we should look at maybe the charge multiplicity that's described by different generators?
Well,
I'm not sure whether I get it correct. Sorry.
Yes. So one of the basic observables which show you that there is certain thermal or thermal-like mechanism of production is taking place. So one of the basic observables which touches this is multiplicities of different hadrons, like pions, kaons, protons, lambda, delta, whatever hadrons you take. And basically there is a question whether they can be fitted with the so-called statistical hadronization model, also in the plus or minus collisions. So
we haven't.
Yeah, go on, please.
Oh yeah, I understand. But here we didn't differentiate the charge hadron multiplicity by like different sources, and we only have this kind of comparison in the backup. But this is just a raw view of the sample, so maybe there can be some correction or something. But basically, the trends are quite good, I would say.
Okay, thank you. Is there, no, I don't see any other hand. So are there more questions? Let me see, I don't see. Okay. I see that someone is enabling party. Do you want to ask a question? I see your mic is open. Okay, probably not. In this case, thanks again for a very nice talk, Yushin. And we move to the next one. So now we have a talk from Achim Geisa. Achim?
Yes, one moment. Do you hear me?
Yes, you can share your video if you want. I see your slides. Just please go full screen. Yeah, now they are full screen.
So you just heard about azimuthal correlations in E+E- collisions. I will report on the first direct measurement of two-particle azimuthal correlations as a probe of collective behavior in deep inelastic scattering in electron-proton collisions at HERA. I will start with an introduction and giving some context. I will then discuss the actual measurement of the long-range correlations in deep inelastic scattering EP events, and will conclude. Now, as you all know, long-range collective effects in heavy ion collisions have been extensively measured, and they indicate that non-perturbative QCD evolution of large parton multiplicity final states can be described by hydrodynamic models. These models also predict the evolution of the initial state towards a particular final state. The long-range correlations in large hadron multiplicity in these final states, they are supposed to keep a memory of this evolution so that studying them one learns something also about the evolution, the initial state and the evolution process. So the question, like I would formulate it, is then, is this hydrodynamic evolution model specific to large initial state systems such as heavy ion collisions? Or does it also apply to smaller initial states such as proton-lead, proton-proton, or even electron-proton? This talk, or E+E-, see, for instance, the previous talk, provided that the final state, as indicated by final state multiplicity, is large enough. In deep inelastic scattering, we have a particularity that the size of the initial state interaction, as seen on the graph on the right side, is actually inversely proportional to the virtuality of the Q-square of the exchange photon, so that we can, by going to deep inelastic scattering, we impose photon virtualities which are significantly larger than the scale of lambda QCD. Another way of formulating the same question as asked above is, do conventional particle physics models describe the observed correlations, in this case in EP interactions, or do we need something in addition? Let me again put a bit of context. The first measurement outside of heavy ion systems was actually done in CMS in 2010. This is a very well-known result. And on this slide, you can see the ridge plot that was explained in detail by the previous speaker. So the feature that was observed in PP collisions is that there is this near side ridge at high multiplicities. And the question is this an indication of hydrodynamic effect similar to the heavy ion case? Or could it be, in some sense, simply a rediscovery of color strings or dipoles as a source of gluon radiation via parton showering, for instance, between semi-hard partons and the proton remnant, as indicated on the plot on the right, which could also create some long-range correlations between, say, a core-hard interaction and the backward connection to the proton remnants. Or maybe the third option, is it just the same QCD described by different approximations in the two cases that actually overlap? So actually, it's not obvious to me that these two effects should factorize. So let's go into that picture a little bit into more detail as far as color strings or dipoles are concerned. So on the top left, you see a graph for E+E- to Q-bar gluon, and was already established in the 90s that when you look at these final states, that you can see differences between particle multiplicities between the quark and the gluon, which do have a color string connection, and the quark and the antiquark, which do not. So clearly such effects do induce observable correlations. On the right, you see the corresponding graph for PP collisions. at LHC. There, the color connections are much more complicated. But in principle, you also have the same effects. Plus, in this case, you have, in addition, correlations between the hard scattering core interaction, if there is one, but plus the backwards connection to the proton remnants, which could induce such correlations. Now, in EP collisions, which is the bottom left, you have the special case that in many events you only have actually one hard final state parton, and you do have the color connection back to the proton, which is in a sense 1/2 of the corresponding color connection in a PP event. And this can be studied by comparison to, for instance, existing particle physics models that model these correlations, like the Ariadne dipole model and the lepto jet set model. That's essentially similar to Pythia 6 that was shown in the previous presentation. And the references for these are given here. And this is also one of the issues that we want to investigate in EP collisions. Coming back to the PP correlations, the proton-proton at CMS. So this is just slices of the ridge plot that was shown before, but for different multiplicities in the vertical axis and for different particle PTs on the horizontal axis. And you can see if in the first row of this plot, well, first you can see that the data, the red points, are not perfectly described by, in this case, the Pythia 8 Monte Carlo. And you can also see that deviations actually already start at very low multiplicities, even at multiplicities less than 35, there are already some deviations. Although a clear ridge structure is only visible, and that was the effect that was the main feature that was highlighted, is only visible at very high multiplicities. But qualitatively, the deviations from the predictions already start at much lower multiplicities. So in EP, we can only access somewhat lower multiplicities, but nevertheless, there might be effects there. A brief excursion to plus E minus. This is the result that was published from the archived Aleph data last year, but it's qualitatively very similar to what you have seen in the previous talk from Bell, so I'm not going to go into details. I would just like to point out that the Pythia 6 prediction, that's the green line on these plots, actually reproduces the data distribution in the study very well. And there is no indication for extra long range correlations. Clearly, well, one of the issues that is not so obvious to me, the Pythia predictions have been tuned on lab data. Of course, not necessarily these specific correlations. Nevertheless, it has been tuned. So maybe the good agreement might partially be due to the fact that such correlations have been just tuned into the parameters available in Pythia, which might be indicated also by the fact that Pythia 8, which has been tuned on other data, agrees a bit less well. But now let's come to electron-proton. Actually, looking at such correlations is not new, although we have looked at them in a different aspect before. So already in 1993, Zeus published the results that are shown on this slide, slide 8, where we look at different angular distributions in the final state, which are partially due to these parton cascades that are being built up between the struck quark, which is indicated in red, and the proton remnant. And actually, without going into details, different parts of the distributions that we measured can be associated to different features of such final states. I would just like to read one of the conclusions in that paper. Namely, in the low X region, that's the low momentum fraction region for the parton that struck, the peak in the hadronic energy flow in the direction of the current jet is shifted towards the proton remnant, with most of the energy appearing between the position of the expected jet peak and that of the proton remnant. So qualitatively, this qualifies as long-range correlations in the sense that there's being discussed. Now the question is now, is this quantitatively described by the models that we have, or do we need something in addition? Actually, in the new analysis that I'm presenting today, we've used the two-particle azimuthal correlation cumulants CN, which are defined as shown in the top right. So just the cosine of n times the azimuthal difference between two particles in the final state. Throughout the talk, we're always using the lab frame, and DIS electrons are always, of course, always included. So the correlations are only measured in the hadronic part of the interaction. And on the right, you see some sketches of what these cumulants mean. So the cumulant C1 actually indicates a directed asymmetry in the data, sort of if you like, in perturbative speak, a monojet-like configuration. C2 indicates an elliptic asymmetry, or if one likes a dijet-like correlation, and so on for C3 and C4. Actually, in contrast to some of the other results that you have seen, our results are fully corrected for single and correlated two-particle reconstruction efficiencies. So the main results that we report are calculated back to generator level, such that they can be compared directly to any theory predictions of any model that you might have. Very briefly for the Zeus detector. So this is a sketch of the inner part of the detector. We have an asymmetric situation. Electrons are coming from the left, protons from the right. And in our definition, the region of the tracker that we're using for this analysis, where we have good resolution for the tracks, is between minus 1.5 rapidity in the electron outgoing direction to plus 2 in the proton outgoing direction. So this is the eta range, the pseudo rapidity range that we use for the measurement. The PT range is between 0.1 and 5 GeV, and the photon virtuality range Q squared is above 5 GeV squared, using a fully inclusive trigger that does not bias the hadronic system in any way. So let's look at some distributions that we get from that. First, the general DIS level distributions. The first one on the left is the reconstructed and generated multiplicity. So in blue, the blue points indicate the reconstructed multiplicity, which extends up to about 30, compared to the red boxes, which are in this case the Ariadne prediction at reconstruction level. And also we indicate the distributions at generator level, which are not so far away from the reconstructed ones in this rapidity range between minus 1.5 and 2. And on the right, you see the distribution of the photon virtuality. There is some inefficiency with respect to 2 at the low end of that distribution, but this inefficiency is very well described by the Monte Carlo that we are using. Then slide 13, same thing for the inclusive PT distribution for all the final state hadronic tracks that are measured in the event. You can see that there is quite good agreement between the data and the predictions at reconstruction level, and that reconstruction level is not far away from the generator level. And on the right side, you see the pseudo rapidity distribution, and this is a bit special because of the EP configuration, which is asymmetric. So the region that we measure is indicated by the blue points and the red boxes. And actually, due to the special kinematics of EP, that region effectively corresponds to the central region of PP or E plus and minus collisions. While the big peak on the right is essentially the proton remnant region that is not covered by our tracker. You see different curves here. The red one is the main one that we use for the comparison. And there, this also includes a diffractive component. You see the diffractive peak, and that modifies the distribution a bit in the proton remnant region. But you can see that in the region that we measure, whether we include or not diffraction makes very little difference. Let me start with the standard ridge plots that has been explained in detail in the previous talk. So you can see that plot on the left for low multiplicities up to 10, and on the right for the highest multiplicities that we can access with our statistics between 15 and 30. The most prominent feature is a kind of a jet-like peak centered at delta phi and delta eta equal around 0. And this is dominated by the single DIS recoil jet, just a jet-like structure recoiling against the electron in the deep elastic scattering event. But there is also an away side ridge, in particular in the high multiplicity events, that is dominated by dijet-like topologies where you have two jets recoiling against each other. And in particular, in on the near side region, there is no indication of any extra ridge, so there is no double ridge structure, even at the highest multiplicities that we can observe. But now let's get to the cumulants that I defined before. So here on the left, you can see the measurement now fully corrected to generator level, and also including the full systematics from different Monte Carlo models. So that we fully cover the potential range that these measurements might have. And so what you see on the 4 plots is the cumulant C1, C2, C3, and C4 for different configurations. The blue one is the full eta range. So this is the short range correlations, and they are obviously strongest at low values of the particle multiplicity. So these plots are shown as function of particle multiplicity, and they decrease towards larger multiplicities. And the long range correlations, which are indicated by the red and the green curves with different cuts on the PT of the particles, they are strongest and negative in the first cumulant. They are a bit smaller and positive for the second. And if you go to very high cumulants, they are consistent with 0. And actually these correlations extend out to where they are observed, extend out to 3, yeah, they're dominant in the first and then they become smaller. Let's look at the same distributions now as a function of the delta rapidity. And here you can see that so blue is for low PT and red is for high PT. On the left, again, C1 to C4. And you can see that the higher PT correlations are more pronounced than the low PT ones. And the negative correlations for C1 or the positive ones of CT extend all the way out to about 3 units in delta rapidity, while for the higher cumulants, things go to 0 at some point. Part of these features, as I will show later are due to dijet-like topologies in the final state. I will get to that. This is the same thing again, slide 17, as a function of average PT of the pair. And again, you can see that the effects, whenever they are observed, they increase towards larger PT values, as one would expect from the correlations in somewhat non-perturbative, in a perturbative regime. But now let me come to the comparison to Monte Carlo models. Slide 18. So these are similar distributions to the ones that I showed before, but now compared to Ariadne and Ariadne predictions, the dipole model predictions in red, and the lepto plus jet sets, or like Pythia 6-like predictions in blue. On the left block is C1, the right block is C2. The first and the second column is as a function of delta eta and average PT again, and then there are different distributions with low PT, high PT, and with or without delta eta cut. And you can see that the C1 cumulant is actually best described by the predictions of the dipole model, the red curve. So this is the left block. It's not perfect, but within systematic uncertainties, the description, we would still call it reasonable. While the C2 cumulant is significantly better described by the lepto plus jet set model, while the Ariadne dipole model does a worse job in this case. Let me state that all these distributions are obtained in the higher charge multiplicities between 15 and 30 particles. On slide 19, you can see similar distributions again compared to Ariadne and lepto, and here the conclusions are similar. In all cases, C1 is better described by the Ariadne model, while C2 is better described by the lepto model, but neither model works well in the full kinematic range. On the bottom, you see an explanation of some of these correlations and they're influenced by jet topologies, showing separately for both lepto and Ariadne the contribution with one or fewer jets. One jet might just be the recoil from the scattered electron. So QCD sets in whenever you have two jet topologies. And actually, many of these correlations are qualitatively explained by such topologies, as you can see from the orange and pink curves, which, however, differ significantly between the different final state correlation models that are implemented in particle physics-like manner. Let me conclude. Two-particle azimuthal correlations in electron-proton scattering, deep elastic scattering collisions have been measured using Zeus data from Hera. This is actually the first measurement in electron-proton collisions. We have used a heavy ion-like analysis approach. Let me state as a side issue that this is a nice example for the value of data preservation, because data taking stopped 13 years ago. And it was actually not at all foreseen to do this kind of analysis, but because it nicely preserved data sets, we can nicely do these analyses even today, and other analyses are also still ongoing. Again, let me make a remark that we don't have open data sets, unfortunately, due to lack of person power, but there is a low threshold for making arrangements with the Zeus collaboration for getting access to the data. And actually, this analysis resulted from such an effort that people actually joined us to specifically do this kind of analysis. So if you have similar ideas or also completely different ones, please don't hesitate to contact us to get access to our data if you like. But now let me come back to physics. The data are reasonably described by existing particle physics Monte Carlo models. But as I've shown, there is room for improvement. The agreement is not perfect. Our data are fully corrected to generator level, so you can directly compare them to any model that you might have, hopefully including also maybe some heavy ion-like effects. I've not shown any attempt to estimate the number of quantitative contribution to hydrodynamic effects, because we're not so sure whether these really factorize or not, but having such models would be very nice in also for electron-proton, maybe also in the context of the upcoming EIC. We have not found any evidence for the occurrence of heavy ion like the hydrodynamic correlation effects on top of the correlations implemented in Monte Carlos. In particular, we have not observed any double ridge-like structure in EP DIS collisions up to the multiplicities that were accessible to us. And that's the punchline that I would stop with. Thank you.
Thank you, Achim, for a very interesting talk. Now we have quite some time for questions. So please raise your hand. I don't see hands yet. Let me check the chat. There's no. While we're waiting, I think it's indeed very, very nice that we could go back both to Zeus and also Aleph data and look at this. Do you have maybe some, I mean, it's, I was wondering if you have some maybe even personal take on the what we see from E plus, E minus, EP, and then going to PP collisions. Do you have any comment on this absence of the reach and the reach in PP?
Well, let me maybe come back to this issue here. To me, actually, it's personally not completely clear whether the effects that are being observed, and in principle, personally, I would expect that if we would go to very high, if we would have enough statistics to go to very high multiplicity, we would also observe some ridge-like effects. That's my personal opinion. Unfortunately, we can't do that with our data. However, it's not clear to me whether such effects would really be an indication for the hydrodynamic model or whether they would be an indication for something else. You've seen in the previous talk, for instance, that the Horwig predictions, which we don't have here, at Bell, they would indicate some deviations that would be similar to some of the hydrodynamic effects. Now, in this case, in that case that was shown, they're not well agreeing with data, but if you would have such effects, it would not be obvious what you would actually attribute them to. So I think that there is a lot of things to be learned, and we're somewhat lacking input from theorists for the EP case. And we would be very happy if there are any theorists in the audience, if they would either comment or make an effort to try to implement some way that we can actually try to quantify whether these things should be factorizable or not. And if yes, if they can be, what we should do in order to actually factorize them, or they could do it on our data since they're fully corrected.
Okay, thank you. Yeah, I fully agree. I don't see any comment from any theory. There's actually now raised hand. So let's go to, I don't know, a question or a comment from Yang Ting.
Oh, it's actually a question and also a comment. So recently, people also got very excited about particle correlations, and they have been improving their simulations. And I think right now they're based on the models that you're using, the dipole model, they improve it to Enganter, and then there are more improved model that are trying to understand the PP two-particle correlations. I'm just wondering if you will be able to try and see what's the prediction they're using their new models in EP collisions. I'm not very sure if they can be directly run in these cases, but it will be interesting to see what they will predict in your case.
Absolutely. Right now, I'm not sure what the current situation is, but for a long time, there were no straightforward predictions for EP from Pythia. Maybe now there are. And if actually there are some predictions that could be directly compared to our data, we would be very welcome to be either getting the predictions directly or being guided how to produce them. That would for sure be very interesting.
Okay, thank you. I think we don't have more questions. Let me check. Okay, thanks again, Achim, for very, very nice results. And we'll move to the next talk, which is the last one before the coffee break. Okay, can you stop sharing your slides, please?
Yeah.
Yes, thank you. So now we have a talk from Adam Trupek, who's going to show us results, Atlas results on correlations in PP and PLED collisions. Adam, if you want, you can share your video as well. And please go also to full screen. Adam, we cannot hear you.
Hello, can you hear me?
Yes, now yes.
Okay, let me turn on the video. Okay.
And we now cannot see your slides. Can you try to share again?
Okay, sorry, I will probably, I haven't used the desktop. Share, desktop.
Yes, and the full screen.
Okay. I am in full screen.
Yes, now we lost again your slides. Okay, now they are back. We see slide 3 now.
Okay, sorry.
Okay, perfect. Yeah, you can start.
Okay, I'd like to present Atlas measurements of correlations in proton-proton and proton-lead collisions. I think we all know that in proton-proton and proton-lead collisions, measurements of multi-particle correlations show evidence for significant collective effects. So in these collisions, there are found similar flow harmonics as in heavy ion collisions, as it is actually illustrated in this example plot. Interestingly, as we can see from this plot, the second order flow harmonics is almost independent on the event multiplicity. So small results from this on small system flow are actually supported by hydrodynamic models. However, alternative models also exist, so more studies are needed to address questions like what is the impact of hard processes, what is the role of the energy loss on the azimuthal anisotropy in small system, and what is the role of the initial conditions. Sorry. Okay, so in my presentation, I will present recent Atlas measurements on correlations in small systems from these 5 analyses listed in this slide, of course, selected results. So starting with the first analysis to get insight on the flow origin in proton-proton collisions, we studied effect of jets in events. So in that analysis, we used the two-particle correlation method with template fitting procedure to remove the non-flow effects from dijets. And this two-particle correlation method was applied to the certain TeV proton-proton data. For events with jets, the charged particles close to a jet by less than 1 unit of pseudo-rapidity are rejected in this two-particle correlation analysis. So such a rejection criterion led us to study the jet effects by comparing VN results in different samples of proton-proton collisions. First, we calculate for reference the flow harmonics in all inclusive events without any jet particle rejection. This is the regular VN calculation as it was done in previous publications. Then we calculate for the same events, for the same inclusive events, flow harmonics with jet particle rejections, and additionally, we calculate flow harmonics for events without jets and for events with jets only. So, and here is the result for V2 as a function of event multiplicity in the left plot for these four samples categories of proton-proton collisions. And in the right, there is the ratio to the inclusive case. So as we can see, the V2 for all cases is very weakly changes with multiplicity. And what we can see actually from the right plot, that for the samples without jet particles, V2 decreases only by 2 to 5%. So the effect of jets is for V2 is quite marginal. So this is corresponding plot for third order flow harmonics as a event multiplicity. In left and in the right is again the ratio to the inclusive case. And as we can see for V3, for samples without jet particles, V3 increases by up to 15% with respect to inclusive V3. So the trend is opposite to that for V2, but nevertheless it is not large. So we can generally we can conclude that long-range correlations in proton-proton collisions arise mostly from the underlying event. Okay, in certain TeV proton-proton collisions, we also obtain heavy flavor flow. This analysis is important because there is a different interplay of radiative and collisional processes in this of heavy flavor quarks compared to that for the light quarks. In this analysis, to measure the heavy flavor flow harmonics, we use the two-particle correlation method. And in this method, we correlate single muons with charged particles. And in the first step, and then we separate these flow harmonics into actually V2 for bottom and charm decay muons using the distribution of closest approach to the collision vertex for these single muons. So this distribution has this nice feature that close to the vertex, we are in the charm-dominated region, while far away from the vertex, we entering the bottom-dominated region. So using this feature, we can extract the V2 separately for these two kinds of heavy quarks. So here is the result, V2 as a function of event multiplicity for charm decay muons and bottom decay muons in left, and as a function of PT for the same cases, plus for charge particles in green. So as we can see, there is a significant V2 for charm decay muons, which is actually consistent with V2 for charge particles. What is also interesting, V2 for beauty decay muons is found to be consistent with 0. So we may conclude that bottom quarks do not participate in this collective behavior in high multiplicity proton collisions. Okay, so in another analysis, charge particle flow, Vn is measured at high transverse momenta in 8 TeV proton-lead collisions. This measurement has potential to actually probe alternative mechanism for the flow origin, like the jet energy loss in quark gluon plasma. So performing such a study is quite interesting. So in this analysis, we again use the two-particle correlation method. It is applied to 3 samples of proton-lead collisions, the minimum bias sample, and 2 jet triggered samples with jet PT greater than 75 GeV and 100 GeV. So it should be mentioned that to lower the non-flow contribution, apart from using the template fitting procedure, we also apply charge particle jet rejection, mainly if associated particles are closer than 1 unit of pseudo rapidity. They are not used in these two particle correlation function calculations. Okay, so here is the result for elliptic flow, second order flow harmonic as a function of P2, as a function of PT for these 3 different samples and for central proton-lead collisions. As we can see, the V2 in minimum bias is actually in agreement with V2 in these jet triggered events at low transverse momenta, but also at high transverse momenta. And what we can see in the region, transition region between 2 and 9, there is a larger flow in minimum bias. So this was studied in detail. This behavior was studied in detail, and it was found that in this transition region, there is larger contributions from particles from underlying event than from hard processes in minimum bias than in 2 other cases. So this is understood, and actually this is interesting to see that flow in proton-lead collisions is finite at this large pseudo rapidity. In the left plot, there is a comparison to a model in which jet quenching is implemented. The model actually quite well describes the V2 and V3. at high PT, and with some underestimate for V2 and also maybe for V3. But what should be mentioned that this model also predicts strong yield suppression, which is not confirmed experimentally for proton-lead collisions. Okay, so to study the impact of initial conditions, we also measured the VN and mean event PT correlations. This was done in proton-lead and lead-lead collisions. This was done using the Pearson correlation coefficient, which is expected or predicted to be very sensitive to the initial conditions in small systems. So actually in the analysis, we use a modified Pearson correlation coefficient rho, in which the regular variances of VN and mean PT are replaced by dynamical variances taken from this theoretical paper. This is done to exclude the multiplicity effects in this regular Pearson correlation coefficient. So the rho coefficient is measured. So the covariance in the numerator of this rho coefficient is calculated using the three sub-events. In pseudo-rapidity, two outer are used for VN determination with a gap, and the central part is used for the mean event PT calculations. Okay, so here is the result of that analysis for rho for V2 as a function of event multiplicity for lead-lead and proton-lead collisions. For each system, the rho is calculated for different PT ranges of particles. Different PT ranges are used to also to study the rho coefficient. But generally, we can see that rho for lead-lead is negative at low multiplicity, and then rise to a value of 0.3 at central collisions, then drops in the most central collisions. And rho for proton-lead collisions is actually negative for the full range of measured multiplicities and show no apparent dependence on charge particle multiplicity. So recently, these results were compared to a hybrid hydrodynamical model, which actually qualitatively reproduces rho in lead-lead. In proton-lead collisions, the model predicts correctly the sign. It's negative, but the magnitude is overestimated. But generally, this behavior at low multiplicities indicates, using the model predictions, that small systems of the initial state are preferred. Small sizes of the initial state is preferred in the small system collisions. Okay, to further probe the effect of the initial state, we also measured the flow harmonics in photonuclear interactions in ultraperipheral lead-lead collisions. So in this analysis, Atlas uses this two-arm 0-degree calorimeter to select these photonuclear collisions. The calorimeter is located in very forward direction, and it can select events like shown here in this event display, where we can clearly see one-sided nuclear fragmentation at lead-going site and rapidity gap and the photon-going site. So this is good candidate for this photonuclear interaction. So selecting this photonuclear interactions and for them we calculate this using the two-particle correlation method. We calculate this flow harmonics. Here is shown the V2 as a function of event multiplicity. And for high multiplicity collisions as a function of PT. As we can see, there is a significant V2 measured in these photonuclear collisions, but it is smaller than corresponding V2 in proton-proton and proton-lead collisions. And this PT dependence of the V2 shows is actually similar to the PT dependence observed for charge for proton-proton and proton-lead collisions. It seems to increase with PT, but okay, there are still large uncertainties in this measurement. Okay, so this brings me to summary. Atlas obtained several results on these correlations in small systems to probe the effects of jets or jet energy loss. The flow was measured in certain TeV proton-proton collisions depending on jet particle rejections, but it was only found to change marginally with jet particle rejection. We obtained the results also for V2 for charm decay muons, which are found to be consistent with light hadrons and significant, non-zero. And interestingly, for V2 for beauty decay muons is measured to be 0. And additionally, we measured finite value of V2 at large transverse momenta in proton-lead collisions at 8 TeV. So to further probe the flow origin, but on the initial state, to study the effect of the initial state, we measured the correlations of V2 and the event mean PT in proton-lead collisions. It is found to be negative and qualitatively compatible with the peripheral lead-lead collisions. Model seems to favor small dimensions of the initial state. And we also measured significant charged particles V2 in photonuclear interactions and ultra-peripheral lead-lead collisions, which is significant but smaller than V2 in proton and proton-lead collisions. Okay, thank you for your attention.
Thank you, Adam. So now we have time for questions. You're perfectly on time. I don't see hands yet. Nothing on chat. So if you have a question, please raise your hand.
I'm sorry, I don't know how to raise the hand.
That's okay. You can go ahead.
So thanks for these very interesting new additions to the investigation. I have a comment and question concerning your jet rejection. On one hand, it's of course very useful to try to see what the effect of jets is. On the other hand, of course, a jet definition is somewhat arbitrary. jet algorithm, and in particular the PT cut. I mean, you put it at 10 GeV if I see it right at the particle,
yes.
at the track level. But of course, you could also equally go to 20 or to 5, and that might change the conclusions. Did you try to vary the jet PT cut?
Yes, we tried to vary it actually from 6 GeV, I think, so very soft jets, to 12 and 15, if I remember correctly, and generally the trends are preserved. No big changes in these plots, for example. But of course, some changes are observed, but very little.
Okay, thank you.
Okay, so I don't see more hands. I can ask a question on slide 10. If you move, please. Yeah, so maybe just one thing. So because this is quite interesting results on this high PT V2 in P-LED, as you commented, we don't see RP-LED being below 1. So this one can say a bit puzzling. But maybe from the experimental side, do you maybe know if there can be any experimental effects that still can account for this observed V2? So maybe what kind of effects did you consider as non-flow? Maybe this kind of.
Actually, the non-flow was here very in detail studied, because first impression is that, okay, this may be non-flow, but we were okay. Already we see samples with different non-flow. We correct for non-flow, of course, in every sample. But these are very different samples in terms of the PT scale. For example, so minimum bias and jets with sample with jets 75 GeV or 100 GeV. These are big jumps, right, in non-flow contributions. And finally turn out to be consistent for all three samples. Of course, we did the standard checks like varying the cuts for pseudo rapidity. Atlas has very large pseudo rapidity coverage at 5 units. 5 units from -2.5 to 2.5, and different jet energy for particle rejections, and the results stayed. So it's puzzling for us. It's puzzling for us why it is finite, because there is no jet quenching observed experimentally.
Exactly. Right? I think it's very interesting. Probably it's something to follow up on from the theory side as well. We have a question from Yuri.
Yes, so thanks for the nice results. I was basically wondering about the slide 13 when you show the interpretation of the whole observable in terms of hydrodynamic models. So when such plots are shown, there is always this question whether the hydrodynamic model actually describes the more basic observables. So I'm not sure whether you're aware of that. So I'm just wondering basically whether the hydrodynamic model actually, apart from this whole, whether it describes the basic PT spectra or multiplicities or the basic elliptic flow in the same setup, so the same energy.
Okay, I am not a theorist, but generally I think the hydrodynamic model is very successful. We have examples, right, when the spectrum in this PT range from 0.5 to 2 GeV is quite well described just by hydrodynamics. here we have also this IP plasma, right? As I understand, this is necessary. I mean, this is added here for purpose to study the dependence on the initial conditions. So okay. My impression is that this hydrodynamics should provide a good description of this basic observables, but okay, this is also a small system, right? So I am actually not fully sure how well, but my impression is that it can describe.
Okay, thank you. You can also follow up on the Mattermost channel on this, if you wish, because we should move on. And thanks again, Adam, for very nice Atlas overview. And please stop sharing your slides. Thank you. And now we have a few minutes for a coffee break. So we start back at 10:36. So thanks again for all the speakers from the morning part of this session for very nice, showing very nice results, and see you in a few minutes. Okay, I see we have few speakers from the next part that didn't test your setups. Do you want to test your setups now? I think there's Paolo, Bedanga, and Krzysztof.
I can try.
Bedanga, yeah, okay. So you may share your video if you wish and show your slides. Yes.
Hi.
Hi, Bedanga.
Try to share. Can you see it?
Yes, please try full screen. Perfect. And can you move the slide? Yes. Okay, it works.
Okay.
Okay, thank you.
Yeah, thank you.
So we can move to next one. I think I heard Krzysztof.
Yes, I am unmuted. Can you hear me well?
Yes, and I can see you. Can you try to show your slides?
Open the first.
Barbara, can you see me?
Yes, but can we try first test Krzysztof?
Yes, I will just try to share.
So it should be the green button at the bottom.
Yes, I have a problem because my computer, which I wanted to use, did not work well. So now I'm trying to. Okay, so now let's share screen. And I have used new one, which.
Yes. Can you try full screen of your slides?
This control should work. No, it doesn't work.
I think that's a browser. That's why it doesn't. Maybe try to open.
Okay, I think I'll solve this. Someone else can try this now. Stop share.
Okay, Paula?
Yes.
Okay, so...
2 minutes?
Yes, I can see you. Can you try sharing your slides?
You see it?
No.
No?
No, I only see your video.
No. Wait a minute. Now?
Still not.
I'm able to share my video, right?
The share screen.
The screen, sorry. Yes, this is what I'm doing.
Do you have two screens? Maybe that's a... Okay, something is coming. Yes, now I can see your browser.
Do you see now?
I see the desktop. Yes, now there's, okay, it works. Yeah, now it's fine. Thank you. So we have everyone. Okay, so we should start. We'll start in 1 minute. Thanks for testing. Yeah, you can leave your slides.
I don't know how.
No, it's fine. It's we can see them.
It's okay.
Now it's okay. It's full screen. Yes.
There's some noise in my laptop. I don't know why.
I see a little bit of noise, but it's not very disturbing. I will just give people a few more seconds since we were a bit late with the coffee break.
Could you briefly remind how one accesses Mattermost?
Yes, I can. Let me post the. I will post the link to the channels. Give me a second. Okay, there should be a link in the Zoom chat.
Thank you.
Okay, so you're welcome. Okay, so I think we can start the next part of the session. We start with talk of Paolo Castolina on universal high energy collisions of small and large systems. Paolo, please start.
Yes. Good morning. Thank you very much for this opportunity to discuss with you about some aspects of the universality in a energy collision for small and large systems, for PP, P nucleus, and nucleus-nucleus collision. As you know, I mean, there are a lot of recent results in PP and PA at LHC and RIC, where there are some similarity, the result of with nucleus-nucleus collisions, where of course the plasma is expected formation, especially for high energy and high multiplicity collision, small system. Okay, here there is reference for a short, brief review, and the result that I discussed today has been presented in this paper in collaboration with Alfredo Iorio, Daniele Lanteri, Helmut Satz, and Martin Spusta. And
Paolo, sorry, we can see your some panel on the side. Could you please close it?
Ah, yeah.
Yeah, sorry.
You mean this one?
Yes, okay, sorry.
Okay. So you see, the first discussion concerned the strangeness production, the universality of strangeness production. There's in universality, the mean transverse momentum in the low PT region, the soft part of the interaction. Then I discussed universality in the elliptic flow. And the final point is how to check this universal trend, the sense that if there is a criterion to say that the universal trend is expected in PP, for example, as for in the case of nucleus-nucleus collision. And starting with this universality in the strangeness production, of course, we have to recall the results of the Alice collaboration concerning the observation of strangeness enhancement in high multiplicity PP collision. And you know, of course, if you look here to the ratio, the yields with respect to pion, the other different species as a function of the multiplicity, you see that indeed the PP and P-LED data are really in the same smooth curve or LED result for high energy and high multiplicity. I have to say that this result, the strangeness enhancement in PP, is a very interesting result, but not completely unexpected, as has been discussed, for example, in this paper by myself with Helmut Satz and Salvatore Plumari few years ago. And it's useful to recall what is the strangeness enhancement. And to do this, we have to start, of course, with the statistical transition model, where we know that the relative hadron abundances in high energy collision is very well described by ideal gas of hadrons resonance at temperature T, which at large energy is almost constant and in good agreement with the confinement temperature, lattice QCT, and biochemical potential. This is true not only for nucleus-nucleus, but also in elementary collision in the proton-proton or Z plus C minus. There is, of course, a caveat in the sense that there is an over-prediction of the strange hadron production, and then there is the introduction of an ad hoc parameter, this gamma S, with gamma X to some power for where this power count, the number of strange quarks in the specific species we are considering. Now, if you look to the data of this strange suppression factor as a function of square root of S, you immediately realize that, for example, if you stay at the square root of S equal 100, okay, this gamma S is equal 1 in nucleus-nucleus, so you have substantially the thermal equilibration, and is much smaller for PP. This is what we usually call this strangeness enhancement. But the point is that if there is some unified description of the strangeness suppression, consider not the energy as the more important dynamical variable to describe the collisions, but some other thermal or, say, pre-thermal variable. For example, if you consider this variable here, which is related to the multiplicity, the number of participants, and the transverse area of the collision, that in one-dimensional hydrodynamical picture is the initial entropy density, okay? You immediately realize that this variable is directly related to the number of partons per unit of transverse area. Of course, since there are large fluctuations in the high multiplicity events, it is crucial to have a reliable evaluation of the transverse area for the different collisions. Of course, we know that also the multiplicity is a function of the number of participants, and also the transverse area is related to the number of participants. So, first of all, we need the evaluation of the transverse area, the multiplicity as a function of the number of participants. This can be done by some Glaude de Monte Carlo for AA for P-led collisions. But of course, reliable evaluation of the transverse area in PP is not easy, because the effective transverse area is really sensitive to the fluctuation of the gluon configuration of fields in the initial state. And so we apply the color glass condensate parameterization of the transverse size as a function of the multiplicity, which has been evaluated in this set of paper here. Now, if you consider this figure, and also if you include much more data than that one consider this figure, but you plot gamma S as a function not of square root of S, but as a function of the variable we are considering, you essentially obtain a rather smooth behavior where PP data, P-led data, and nucleus-nucleus data are essentially consistently described by the unit curve with gamma S equal 1 in all high energy collisions, I would say all high energy and high multiplicity collisions. So from this point of view, you see that there is a rather universal behavior that in some sense is model dependent, but it could be that there is a model dependent scheme because of course gamma S is a parameter of the statistical organization model, and you can have also different models in the sense that you can change the resonance you include in your scheme, some cut in the mass and so on. So it's better to consider something which is completely model independent, just considering the Alice data plotted as a function of the multiplicity, and to plot the same data as a function of the variable we are considering, which is the variable related to the parton density in the transverse plane, and you see that indeed there is a completely smooth behavior between the PP, P-LED, and LED results. So from this point of view, this variable that we are considering gives an understanding of the universal behavior of the strangeness production in small system and in large system. Now, the problem is to see what happens, of course, in other, at the moment, coarse-grained dynamical result. Another point is this concern the average PT in the low transverse momentum region. For high PT, there is another paper where the possible scaling is discussed, this paper here that you see here. But if you plot again the average PT, okay, with this cut here, for small system and for large system, you again see that indeed there is a quite good and smooth behavior for small and large systems. The same result is obtained if you consider the cut at 2 GeV, for example. So this is another indication that some universal dynamic is at work in high energy multiplicity event. And the other part concerns the universality in the elliptic flow. Because of course we know that the geometric picture, the almond-like shape, is not realistic, is not a realistic description of the initial state of the collision, because one has to take into account the position of the individual nucleons that participate in the elastic interaction. Okay? So one has to consider the regular shape, the event-by-event fluctuation, and therefore one define what is called the participant eccentricity. Okay, but the participant eccentricity is also directly correlated with the transverse area, which is not the transverse area usually evaluate in the geometrical picture, let's say, for the reaction plane eccentricity. This is a schematic view in the sense that we have different position of the nucleons, and then you take into account this different position. This is a more realistic picture, and you see that the transverse area associated with this initial condition, and has a fluctuation with respect to the almond shape, and then there is a transverse area which is associated with the participant eccentricity. Well, these are the CMS and Phobos results where the elliptic flow divided the participant eccentricity is plotted versus the number of participants. Okay? When essentially you divide V2 by the participant eccentricity, you try to remove, if you like, the dependence of the initial shape and the nucleus collision, and also some fluctuation related to the nucleon's position. Okay, and you see that this ratio, okay, does not scale as a function of the number of participants. On the other hand, the same collaboration considered now a different variable, which is the variable I discussed before, which is the multiplicity, okay, divided by the transverse area associated with the participant eccentricity. And if you consider this variable, okay, you see that there is a smooth behavior, okay, let's say unique behavior going from low energy to high energy nucleus collision. Now the question is, what happens for proton-proton? Oh, the problem with proton-proton is not easy, of course, because you have to evaluate the transverse area associated with the participant eccentricity for a small system. And I mean, there are suggestion models in these two papers, for example. And if you consider the value of the transverse area associated with the participant eccentricity here, you can also plot the results for proton problem. And if you plot essentially the elliptic flow divided now the participant eccentricity as a function of this variable, okay? This S is the transverse area related to participant eccentricity. You see that the proton-proton data, again, are in this kind of, this kind of smoke curve, okay, with the large systems behavior. So there is some kind of universality in this ratio if plot against this versus this variable. And you can see what is the effect of the reliable calculation of the transverse area. Because if you plot the same variable, not the same ratio as a function of this variable, but not using the transverse area associated with the participant eccentricity, but the transverse area associated with the geometrical, let's say, overlap, okay? Then you see that the scaling, there is no scaling anymore. So there is a crucial role in this variable that you are considering of the transverse area, which means that from this point of view, what really counts in this dynamic in going from a small to large system is the parton density in the transverse plane. And if this is true, is rather simple to find the criterion where you can expect more or less, let's say for this cross-grain variable, the same kind of behavior. Because since the crucial dynamic of variable is this entropy density in the parton density in the transverse plane, if you have, for example, the same value of these two ratios, this for nucleus, and this one for PP, you should expect a similar behavior. Which means that, for example, if I consider lead at 5 TeV, okay, for this centrality, by Glauber Monte Carlo, I know what is the multiplicity in this case. By Glauber Monte Carlo, I evaluate the transverse area, and then I know the value of my dynamical variable, okay? And so I can ask, what is the multiplicity in PP, which reproduce this value here, and then I obtain the multiplicity, which is almost 100. So in this condition, at multiplicity, PP multiplicity of about 100, I expect something which is very similar in this cross-grain variable, but also maybe in other ones, similar to the lead centrality result at 5 TeV. This is, of course, can be done for centralities, but also for any different values of the energy. So from this point of view, there is a criterion to try to understand when one can expect the same behavior in large system and a small system. So I can conclude my discussion recalling that this is the crucial variable that one has to consider to compare small and large system, rather than simply multiplicity. This is what we have analyzed these variables, of course, but there is a lot of work that has to be done. And we know, according to this criterion, what is the multiplicity, for example, in proton-proton, where the universal behavior is expected. And I would like to conclude with something concerning the plus-minus result. Because you see, the plus-minus, the figure that you see here is the plot of the strangeness suppression factor gamma S as a function of square root of S. Okay? Now, differently from nucleus to nucleus and PP, when you increase the energy, of course, we are discussing energy something like 200 square root of S, then you have that the gamma S decrease. There is no enhancement of strangeness production in the plus-minus data that we know. But on the other hand, as has been discussed in the previous talk, there is also no signal of something like a flow in the plus-minus. And according to this criterion, the answer why we don't see this, the enhancement in plus minus of this energy, and there is no like flow behavior in plus minus, is because not the multiplicity is too small, but because the density of particle in the transverse plane is too small. The definition, of course, of transverse plane plus minus is a tricky point. That, there is a paper in collaboration with Daniele Lanteri, thermostats in progress concerning the plus minus. Okay, so that's all. Thank you very much. The postcard from, at least the postcard from Prague.
Thank you. Thanks, Paolo. So we have a lot of time for discussion. So I see raised hand by Federico, please.
Yes, hello, can you hear me?
Yes, yes.
Okay, ciao Paolo, this is Federico. I have a comment on your slide 4 where you show the gamma S as a function of root S. And it seems to me that in this picture you have for low root S, you have gamma S values which are calculated over full rapidity, whereas from RIC on you have central rapidity, the and the eta. And actually my comment is that if you do the same at SPS as you do at RIC and the LHC, namely you use the and the etas at central rapidity, actually gamma S is equal to 1 everywhere, even at the SPS. That's the comment.
Yeah, this I understand. But you see, this is the reason why this is the reason why in this analysis, then we immediately decide to move and to consider directly the ratio, your data essentially, the ratio of the yields. Because you see, this result here is model independent.
I understand that. No, my comment was on the way you presented the lower energy data, not on our.
Okay. Mm-hmm.
Okay, thank you. More questions, comments to Paolo? Let me check if there's something in the chat. There's nothing in the Mattermost channel. So I don't see more questions. So thanks again, Paolo, for very, very interesting talk. I think it was probably the idea was very clear to people. And then we move to the next talk. Could you please stop sharing your slides? Yes, thank you. Thanks again for the talk. And now we move to Vedanga Mohanty, who will talk about spin alignment measurements of vector mesons with Alice at LHC. Vedanga?
Yeah, can you hear me?
Yes, and I can see you. Could you please go full screen? Yes.
Okay. So
yes, you can start.
Okay, so good morning and good afternoon. And thank you, thanks to the ICHEP 2020 for giving this opportunity to talk. So the title of my talk is Spin Alignment Measurements of Vector Meson with Alice at LHC. The outline of the talk is as follows. First, I will give a very brief introduction to high energy heavy ion collisions. Special focus will be on initial condition of angular momentum and magnetic field. Then I will be presenting the results on spin alignment of vector mesons. After that, we'll have some discussions, and then I will end the talk with a summary and outlook. This is based on the recent publication from Alice in PRL. So two heavy ions accelerated at relativistic speed come and collide at non-zero impact parameter. A torque is imparted to the participating matter. As a result, a high angular momentum is imparted to the system. Similarly, these nuclei have charged particles, the protons, when accelerated at relativistic speed, can also impart a large magnetic field to the participating matter. Both this angular momentum and the magnetic field are expected to be perpendicular to the reaction plane, a plane subtended by the impact parameter and the beam axis. Now let's see what is the magnitude of these initial conditions one expects from theoretical calculation. On the right-hand side is the angular momentum J in units of h bar plotted along y-axis as a function of impact parameter for a representative system of gold and gold collisions at 200 GeV. For central collisions, small impact parameter, or peripheral collisions, large impact parameter, the angular momentum values are small. For mid-central collisions, they can be as large as 70,000 to 80,000 h bar. Remember, angular momentum being a conserved quantity, the effect is expected to be felt throughout the evolution of the system. On the lower right-hand side is the magnetic field in unit of MeV square as a function of time. As a representative system is gold and gold collisions at 200 GeV for various impact parameters. The magnetic field is quite large, of the order of 10 to the power 18 Gauss, and dies down rapidly. Now the question we ask is, this large initial angular momentum, does it have any observable consequences in heavy ion collisions? We expect that the angular distributions of decay daughters of vector mesons could be affected if there is spin orbital angular momentum interaction. The vector mesons which we have studied are K star and phi. These are spin 1 particles whose properties are listed on the left-hand side. Now, the angular distribution that we are talking of is constructed as follows. We have a quantization axis which can be perpendicular to two kinds of planes. Production plane subtended by the momentum of the vector meson and the beam axis, or it can be perpendicular to reaction plane, impact parameter and beam axis forms the plane. We go to the rest frame of the vector meson where the decay daughters are back to back. The angle made by the decay daughter with respect to the quantization axis is what we are interested in. As theory says that this angular distribution, as shown in the green box, is related to the spin density matrix element rho 00, that is the 0th component of the 3×3 Hermitian spin density matrix. Now rho 00 tells us what is the probability that a vector meson is in a spin state 0. It's a spin 1 particle. It can be in state -1, 0 or 1. All states are equally probable. So in absence of any interactions, rho 00 will be 1/3. If I substitute rho 00 1/3 in the equation, then the angular dependence drops off. The angular distribution is uniform or flat, and that's what we call as no spin alignment. If the vector meson prefers a particular spin state, for example, due to angular momentum and spin interaction, then rho 00 will deviate from 1/3 and you will have a non-uniform angular distribution. That's what we are looking for in the experiment. Now let's see what theory qualitatively suggests about this rho 00. Based on this publication, if the angular momentum, which is large in the initial stages, polarizes the quarks and the quarks subsequently hadronize by the process of recombination to form vector mesons, then the rho 00 as a function of transverse momentum of the vector meson is as shown on the left-hand side. It's a low PT phenomena. The rho 00 takes value lower than 1/3 or no spin alignment case. And then at high PT, it reaches 1/3. Now, what about centrality dependence? That is shown on the right-hand side, rho 00 as a function of impact parameter. Remember, the angular momentum values are small for small impact parameter and large impact parameter. It was maximal for the mid-central collisions, and that is what the rho 00 is expected to qualitatively follow. Now, there are two kinds of vector mesons, but they differ in some properties like lifetime, rescattering of the daughter decay particles, and mass, etc. And that leads us to an expectation that the signal will be a little larger for K star compared to phi meson. Now, what are the other physics processes which can affect this value of rho 00? These includes vorticity, and these are listed here with the reference. I'll not go through in detail. These include vorticity, magnetic field, the kind of hadronization, And also recently, a technique called phenomena proposed is coherent mesonic field. Now with this introduction, let's come to the measurement where we use the ALICE detector at LHC. The sub-detectors which are used for particle identification are the time projection chamber and time of flight detector. For momentum measurement, we use the TPC and the inner tracking system. And for the event plane measurements, we make use of the forward V0 detector. Just to give an idea how well ALICE reconstructs the charged particles or identifies the charged particle, a representative plot from TPC, specific ionization energy loss as a function of momentum, is shown on the top right. This is for PP13 TeV. And you can see how beautifully we can separate out the charged particles. This has now taken its place in the PDG in 2018. Just to tell you all how the event plane, how well we reconstructed, the event plane resolution as a function of collision centrality is in the bottom plot. 0 corresponds to central collisions, 80 corresponds to peripheral collisions, and where we expect the signal to be maximal is shown in the box, and the V0 event plane resolutions are of the order of 0.7 to 0.8. Now, what is the data set which I'll present today? Proton-proton collisions at 13 TeV. It acts as a baseline to the lead-lead results at 2.76 TeV. Measurements are at mid-rapidity. We will look at vector meson K star and phi, as well as spin zero K short. That also acts as a baseline measurement. All these measurements are reconstructed by invariant mass technique. Hence, combinatorial background has to be subtracted, and that's done through mixed events. All the results are corrected for efficiency and acceptance. We will present results normal to the production plane and event plane. We will try to randomize the event plane direction, and hence that will also act as a baseline. The event plane resolution will be corrected for the ρ00 value as by the expression given at the bottom, and details are in that reference. Now we start with first reconstructing the vector mesons. K star phi, the top panels are for lead-lead collisions, bottom panels are for PP collisions, the left-hand side are for K star, right is for phi. The invariant mass of K pi and Kk. These are after removing the combinatorial background, so there is some residual background present. To extract the signal for K star, this distribution is fitted to a Breit-Wigner and a polynomial residual background. To obtain the yields for phi meson, it's fitted to a Voigtian function plus polynomial. Voigtian is a convolution of Breit-Wigner and a Gaussian, where the width of the Gaussian is the mass resolution. Phi is a narrow resonance. Now, we obtain these yields in a particular PT bin and in a cos theta star bin. And then these yields are subsequently corrected for efficiency, corresponding efficiency and acceptance values. The signal, of course, is much better in terms of signal to background for PP collision compared to lead-lead collisions. Now, once we have the corrected angular yields, we have d and d cos theta star plotted in y-axis as a function of cos theta star. The red points are results for K star for measurements with respect to event plane. The solid lines are statistical uncertainties, boxes are systematic uncertainties. You can already see that the angular distributions are not uniform. The line is a fit to the data following this equation from where we will extract the ρ00 value. Now let me superpose the results with respect to production plane. Similar trend is observed. It's non-uniform. Now let's look at the baseline from PP. Remember, PP doesn't have large initial angular momentum, and we see that the angular distributions are flat. Now what about the spin zero K0 short? Here are the results for both with respect to event plane and production plane, and they are also flat in their angular distributions. Now let's see how the extracted ρ00 varies as a function of transverse momentum of the vector meson. Y-axis is ρ00, x-axis is PT. Results are shown for K star with results with respect to event plane. The dashed line is no spin alignment, or ρ00 1/3. Clear deviation is seen at lower PT. At high PT, consistent with 1/3. The results for production plane in blue, similar trend, high PT, no spin alignment, low PT, deviation from 1/3. For PP collision, the baseline measurement, no initial angular momentum, large values, and we find it's rho 0, all the measured PT range is consistent with 1/3. For K0 short, spin 0 particle within uncertainties, consistent with no spin alignment or rho 0, 1/3. Let's look at it in a little bit more in detail. Here is the rho 0 plotted as a function of PT. The left-hand side are for K star, right-hand side is for phi mesons. Upper two panels results with respect to event plane, middle respect to production plane, and lower plot with respect to random plane. Clearly, we see spin alignment effects for spin 1 particles, K star and phi. No spin alignment observed for K0 short, spin 0 particle, magenta are the results. No spin alignment observed for proton-proton collisions, the black data points. And for random plane, also no spin alignment observed. Let's look at the centrality dependence. Rho 0 plotted in y-axis as a function of average number of participants in the x-axis. Large number of participants, central collisions, small impact parameter, small average participant peripheral collisions, large impact parameter. Upper two panels are for production plane, lower two panels are for event plane. The left side are for K star and the right side is for phi meson. Each panel has blue data points for high PT, red data points for low PT. We find maximum deviation from no spin alignment for mid-central collisions and for low PT at the level of 3 sigma for K star, 2 sigma for phi mesons. High PT, rho 0 consistent with 1/3. As you go to peripheral or central collisions, rho 0 values approach 1/3. Let's now try to discuss these findings vis-a-vis some theory expectations. Let's again look at the centrality dependence, K star rho 0 as a function of average number of participants on the top left-hand side plot. The published ALICE results are shown in red. Recently reported lower energy RIC results are shown in blue and black. The trends are similar both at RIC and LHC. Now, I will take you back to the initial slides where I had shown angular momentum as a function of impact parameter. Let's look at the trend. For central collisions, high end part, or peripheral collisions, lower part, the angular momentum are small, mid-central, large. And that's the trend also seen in rho 0, maximum deviation for mid-central collisions. For PT dependence, bottom plot, K star rho 0 versus PT, similar trend at RIC, lower energy, and at LHC, our results. This transverse dependence of rho 0 is consistent with theory expectation that there is polarization of quark in presence of initial angular momentum in heavy ion collisions and its subsequent hadronization by process of recombination. Now let's see how our results compare with respect to some other hyperon polarization measurements. On the left-hand side is hyperon polarization as a function of collision energy. The polarization values decrease as one increases collision energy. Now, the results are the polarization percent is 5%, and hyperon polarization goes as the quark polarization. Now, on the other hand, the rho 0 values go as square of the quark polarization. We do not see within the uncertainties energy dependence, and the rho 0 values tends to give a larger value of quark polarization, and this has to be understood. On the lower side are K star and phi rho 0 as a function of average end part for RIC and LHC. K star, RIC and LHC follow similar trend, but for phi there is opposite trend. And this also needs to be understood. So I will come to the summary. We have shown the first evidence of spin alignment of vector mesons in high energy heavy ion collisions. Both RIC and LHC observe the phenomena. The measurements are coupled to the event plane and vanishes when we randomize the event plane. This suggests it is related to initial angular momentum effects. No such spin alignment is observed for proton-proton collisions using the same analysis and detection techniques. No spin alignment is observed for spin zero particle like K-short in heavy ion collisions. Let me present a brief outlook. These experimental measurements are very interesting and fascinating, and they do pose challenges to theory. For example, how to understand the polarization values from lambda hyperon and vector mesons simultaneously. There is a puzzle here. How to understand the difference of rho 00 for phi mesons at RIC and LHC. Of course, these may need theoretical developments in relativistic spin hydrodynamics and including conservation of angular momentum in models. On experimental side, we can increase the precision of measurements by collecting high statistics data. This may also allow us to sensitivity to initial magnetic field. Then we will try to look at differences in observables for lambda and anti-lambda, or charge K star and neutral K star, which differ in magnetic moment by factor 7. We have already started looking in ALICE for high statistics 5 TV data. The preliminary result is shown for rho 00 as a function of PT on the right-hand side. And we see the signal, and it seems to be of similar level as lead-lead 2.76 TV. I will end the talk by saying that establishing and having a proper treatment of initial conditions in heavy ion collisions could have impact on the physics and the discoveries that we make in this area. Thank you very much.
Thank you, Pedanga, for a very nice talk. And I see we have already first question from Helena, please.
Hi, good morning. Thanks for the very nice talk. It is very interesting indeed. My question is, do you plan to extend these measurements to JPSI?
Yeah, I think we are already working on it. Yes.
Yeah, because already in this conference, Alice has presented the results on the JPSI polarization at forward rapidity. And there is a hint of for modified polarization in lead-lead at forward rapidity.
Yes.
Could be interesting to check.
Yes,
within
definitely.
This scenario.
Definitely, we will. I mean, we're looking at it, and yes.
Okay.
Thank you. Please raise your hand if you have a question for Pedanga. I don't see more questions. I just checked the Mattermost. So maybe just a quick question, Pedanga. So you say that you are working on 2015-18 data set. So you plan to basically redo all the measurements that you've shown for the lower energy and check. So even without going to run 3, we should already have better precision, right?
Yes. Yes.
Okay, thank you. So let's wait for, we have still time, so let's wait for a few seconds. And if I don't see a hand, then we'll move. Okay. So thanks again for a very nice and clear talk, and we will move to the next speaker. So the next speaker is Paraskevei Ganotti.
Hello, good morning.
Yes, I can, yes, and please start sharing your slides. Okay. And the talk will be on hadronic resonance production measured by Alice at the LHC. Yes, I can see your slides. You can start your presentation.
Okay, thank you very much. So I'm going to present some recent results on hadronic resonances measured by Alice at the LHC. I will start with a brief physics motivation and a brief description of the Alice detector, and then I'm going to present the results on the resonances, more specifically the PT spectra in proton-proton, proton-lead and heavy ion collisions, the PT integrated yields and mean PT, particularly given the ratios. Then I will focus on the phi meson and will discuss some nuclear codification factors, and at the end the summary. So resonances are ideal probes to study the hadronic phase, which is formed in nucleus-nucleus collisions because they have lifetimes comparable with the fireball lifetime. And in this table, we can see all these resonances measured by ALICE having different decay times from 1.3 Fermi to 46.4 Fermi. So at the chemical freeze-out, the yields of long-lived hadrons are fixed, and then between chemical and kinetic freeze-out, there are elastic collisions taking place. For example, K-star resonances might be formed from its constituent particles, and this is called regeneration. But on the other hand, a K-star resonance which decays to a pion and a kaon, the pion, for example, can scatter with another hadron in the medium, or can interact with another pion, such as to form another resonance. In these cases, the K-star is lost, and this is the so-called rescattering. The yields then on the kinetic freeze-out depend on the resonance lifetime, on the lifetime of the hadronic phase, the yield, the chemical freeze-out, and the scattering cross-section of decay products. Here is the ALICE detector. You have already seen it, and I will mainly focus to the tracking detectors used for the resonance reconstructions. Namely the inner tracking system, the time projection chamber, the time of flight. All these detectors provide tracking and PID. And we have also two scintillator arrays, V0A and C, placed on either side of the interaction point with self-trigger and centrality or multiplicity estimator. In ALICE, we have collected all these data during run 1 and run 2, all the collision systems and energies available. So the resonances are reconstructed via the invariant mass technique, and the uncorrelated background is calculated via the event mixing. And then for the decay daughters, we have the PID from these three detectors as I mentioned above. And after the event mixing background, there is a remaining background, all this distribution that you see, for example, here. Here is the invariant mass of lambda pi. This is a mixed event subtracted. And this distribution is fitted with a Bright-Wigner and a residual background. This is for sigma star plus, measured in 0 to 10 centrality class at between 3.5 and 4.5 GeV in PT. And this plot is for sigma star minus in 30 to 50 centrality class, and PT between 2.5 and 3.5 GeV. This is a new measurement in ALICE. These are sigma star plus and minus in lead-lead collisions at 5.0 TeV. So in ALICE, we have measured the resonances in lead-lead collisions at 2.76, 5.02 TeV, but also in xenon-xenon collisions. And here you can see the rho 0, the lambda 1520, and the Xi star in different centrality classes in lead-lead collisions at 2.76 TeV. But we have also K star and phi in lead-lead collisions at 5.0 TeV in different centrality classes. This is a measurement that is published last May. And here we see the PT spectra for sigma star plus and sigma star minus measured in three centrality classes, 0 to 10, 30 to 50, and 50 to 90, up to 9 GeV, with a very good statistics. But we have also PT spectra in proton-lead collisions at 8.16 TeV. This is K star and phi in different centrality classes. And in the bottom plots, we see the ratio to the non-singlet diffractive event class. And what we observe is that the slopes of the hadron PT spectra increase with increasing multiplicity. This is qualitatively similar to the behavior we see in lead-lead collisions, and the color reconnection mechanism can lead to collective flow-like effects even in small collision systems, so this is under investigation. But we have also PT spectra of K star and phi in the proton-proton collisions at 13 TeV, where we see again this hardening of the PT spectra with increasing multiplicity. For PT greater than 5 dB, we see that in all cases, all the shapes are similar across multiplicities. Now for the PT integrated yield, in these two plots, we see for K star and phi, the d and dy, as a function of the charged particle multiplicity in proton-proton collisions at 13 dV and 7 dV, and proton-lead collisions at 5.02 dV. We see that the d and dy exhibits an approximate linear increase with the charged particle multiplicity. And for a given multiplicity, K star and phi production does not depend on the collision system or energy. Comparing to models now, for K star 0, we see that the EPOS and the Pythia 8 without a color connection can describe the data. However, for phi, phi is slightly overestimated by EPOS and underestimated by Pythia tunes. In this plot on the right, we see the d and dy for K star 0 as a function of the charged particle multiplicity in lead and xenon collisions, where we see again that the K star production is driven by the multiplicity. For the mean PT now, we see the K star 0 and the phi in these collisions mentioned above. Again, where we see that the mean PT values for proton-proton collisions follow approximately the same trend no matter what the energy is. And comparing the mean PT values in proton-proton and in proton-lead events in both K star 0, we see that the mean PT values for K star 0 rises slightly faster in proton-proton than in proton-lead collisions. This is the mean PT, again, as a function of the charged particle multiplicity for K star and phi, but for heavy ion collisions, lead and xenon, where we see also that in heavy ion collisions, similar trend in the evolution of mean PT is observed. Sticking to the mean PT, here we compare the mean PT as a function of the charged particle multiplicity for protons K star and phi, in different systems and energy. So what we see here is that in central lead collisions, ions K star and phi have a similar mean PT, which is expected from the thermodynamic behavior of the system. We see again more clearly here that the mean PT in small systems increases faster than in heavy ion collisions. And if we focus here in this region, we see that the mass ordering is broken in proton-proton, proton-lead, and even peripheral lead-lead collisions. Coming now to the particle yield ratio, here we see the yield ratio of sigma star to the more stable lambda. And from data from ALICE, the red points are from ALICE. This is proton-proton, these 3 points are proton-lead, and these 3 points are lead-lead events. The gray points come from star, lead-lead, proton-proton, the gold and central gold-gold collisions. So we see that a suppression of sigma star is observed for the first time in lead-lead collisions, and neither EPOS nor the thermal model agrees with suppression we see. On the other hand, in small systems, it seems that Pythia 8 is in agreement with the data. Plotting here more particle yield ratios for different resonances and different decay times, we see in general that there is a tendency for the yields to decrease with increasing charged particle multiplicity. Especially for rho 0 K star, this tendency exists also in small systems, something that we don't see for sigma star and lambda. And for xi star over xi and phi over k, it seems that there is no significant multiplicity dependence across the different collision systems. In general, we see that in most cases, EPOS3 with URQMD describes at least qualitatively the data. For the PT differential yield ratios, here we see the K star over K and the phi over K as a function of PT in central lead-lead collisions, peripheral lead-lead collisions, and proto-proton events. What we observe is that the ratio K star over K in central collisions is lower than in peripheral and proton-proton collisions, which is an evidence of rescattering in the hadronic phase. And also what we observe is that this rescattering is mainly concentrated in the low PT region. In intermediate PT region, we see here for phi enhancement in lead collisions comparing to peripheral and proton-proton. Now we focus on the phi measure and we plot here the ratio of the yields of particles with different units of straightness to the pions as a function of the charge particle multiplicity. In all cases, there is a small smooth evolution with charge particle multiplicity in all available collision energy in systems. As we know, the straightness enhancement increases with the straightness content of the particle, and phi is composed to an SS bar pair, so it is very interesting to see how this resonance is behaving. For this reason, we plot the yields of the phi over pions that have no straightness at all. And we see that in central lead-lead collisions, this ratio saturates and it is consistent with thermal model predictions. But this ratio also increases with multiplicity in small systems. And this is not expected from canonical suppression. And what I mean is in this plot, we see not the phi over pi, but the phi over k. And this is the canonical suppression model prediction that we see that this model predicts an enhancement of phi in lowest multiplicity, which is not seen in our data. Here we plot also the phi over k. K has 1 unit of straightness. This ratio is almost flat. And this means that the phi behaves like a particle with a straightness greater or equal to 1. More on ratios, we plot here the xi over phi. Xi has 2 units of straightness, and we see that in small multiplicities there is an increase, and then this ratio saturates. And from all these observations, we conclude that the phi has an effective straightness of 1 to 2 units. Now, in this plot, I'm discussing the nuclear modification factors in lead-lead events at 5.02 TeV 0 to 10 centrality class for pions, kaons, protons, K star, and phi. We see that at the intermediate PT, there is a hint of mass ordering above the mesons, but protons do not follow this trend. And at high PT, the suppression is the same within the uncertainty for all the light flavor hadrons, which means that the energy loss has no flavor dependence. In a list, we have measured more resonances, and I'm going to show you some recent work from F0 reconstruction. F0 is a resonance for which we don't know its core contents, so it's very interesting. And this and here you can see the PT spectra of F0 in proton-proton collisions at 13 TeV. And also we have measured Xi 1820. This resonance is also very interesting because the fast sum collaboration from lattice QCD simulation has shown that in the presence of unbroken higher symmetry, the positive and negative parity by baryonic channels are degenerate. And there is then a parity doubling. Here we can see the mass as a function of temperature normalized with M plus at the lower temperature, and we see that there is a change of Xi star minus with the temperature, while this Xi star plus remains flat. So what we expected to see experimentally is a mass shift, or with broadening, or a change in the yield ratio between Xi star Xi 1820 and Xi 1530. And on the bottom plots, you see the first attempt to extract the Xi 1820 peak, and we see here that we have a clear signal. So summarizing, Alice has provided a comprehensive study of resonances in proton, lead, and lead collisions at all available energies and systems, with very interesting results. We have measured the sigma star plus minus in lead collisions at 5.0 TeV in 3 centrality classes. We see the hardening of the PT spectra in small systems, not only in heavy ion collisions. Resonance production is independent on the collision energy system and is driven by the event multiplicity. The mean PT shows a steeper increase in small system, and similar mean PT is measured for pions, K star 0, and fine central regions. Resonances rho 0, K star 0, sigma star plus, and lambda star are suppressed in most central collisions with respect to small collision systems. And the sigma star plus minus suppression is seen in central lead collisions for the first time. Phi, which has a relatively large decay time, is not suppressed, and it has an effective strangeness of 1 to 2 units. The parton energy loss at high PT species independent, as we saw from the RAA measurements, and more resonances are being explored, like F0 and Xi 1820. Thank you.
Thank you, Paraskevi. So we have plenty of time for a discussion. So please raise your hand if you have a question. I'm checking if there's chat. So just a reminder, one can ask also a question or discuss on the Mattermost chat. Okay, there's a hand. Yep, go ahead.
Hey, so thanks for nice results. I'm actually wondering, is there a simple explanation why those resonances are suppressed in the central events as respect to small systems?
This, at least for the K star, we have seen that this is an effect of rescattering. As I showed in the first slide, this is an effect that we expect to take place in the hadronic phase. So the scattering of the K star, the lower yields that we observe for the K star, for example, is an effect of scattering. But for the other resonances, we expect something like that. But of course, for the moment, there is no unique explanation, I think, for that.
Thank you. So we'll wait for more questions a bit. Okay, I don't see more hands up. So thanks again, Paraskevi, for very clear talk and a lot of results.
Thank you very much.
Thanks. And we are going to move to the next talk, which is by Hanna Sproszczyk.
Hello.
Yes, I can hear you and see you.
Let me share my screen.
So she'll talk about geometry and dynamics in heavy ion collisions seen by the femtoscopy method in the STAR experiment.
Yes.
Can you go full screen?
Yeah. Yes, can you?
Yes.
Okay. So good morning, ladies and gentlemen. This is my pleasure to discuss geometry and dynamics in heavy ion collisions seen by the method of femtoscopy. I would like to take this opportunity and express my appreciation to the organizers to give me a chance to speak about this STAR results. So this is a short outline of my presentation, which is as follows. After a short introduction, I will move to the main part, which consists of 3 calls. First one, we discuss interactions. The second one, geometry, and the last one, dynamics that we can determine from femtoscopic studies. So let me briefly introduce. So here you may see very well-known scheme of heavy ion collision. So first we have a pre-collision state, then the collision itself, then system starts to expand, then hadronize, and we have freeze out. And the point is that with traditional HBT method, we can probe characteristics of this source and parameters related to expansion. Like, for example, we can determine particle emission duration or system's lifetime, or also the kinetic temperature of the source. And also, of course, with two-particle correlation, we have access to geometrical sizes. These are called HBT parameters, but one should remember that with traditional HBT method, we don't probe the whole source itself because we are sensitive to the range of interactions. So the point is that we measure so-called region of homogeneity. So as I said, with femtoscopy, we can probe the source and its characteristics. And I would like to remind you that we probe sources of the order of sizes 10 to the minus 15 times 10 to the minus 23 seconds. And these observables are absolutely, that cannot be accessed directly by any method. And with help comes method of femtoscopy, which is inspired by the method from astronomy, Hanbury, Brown, and Twist interferometry. However, I would like to pay your attention. There are main differences between these two methods because in femtoscopy, we deal with sizes of the order of femtometers, while in the method of astronomy, we measure sizes 10 orders bigger in magnitude. Another important difference is related to measured quantities, because in astronomy, we are sensitive to intensity signals registered by detectors, while in heavy ion collisions, we measure particles' momenta. And the most important difference is that in astronomy, we measure angular sizes of stars, while in heavy ion collisions, we probe sources and its sizes. So here you may see an example of source, and we would like to probe its characteristics with femtoscopy. So here you can imagine 2 points that emit particles. These particles are emitted with their momenta P1 and P2. The point is that to understand that we cannot access directly emission points, but what we can measure is related to particles' momenta, and thanks to particle correlations, we can probe these points of emission. So definition of correlation function is that we determine a probability when we observe 2 particles together, the same time, the same place. And then we normalize this by probability that we observe these 2 particles separately. Of course, in the experiment, we construct correlation function in quite different way, because we deal with distributions of particles momenta, or into numerator, we put pairs of particles coming from same events, same collisions, and then we normalize by distributions of particles coming from different events. So here, as I already mentioned, we probe source and its characteristics due to thanks to correlations, and it's important to understand what is responsible for these correlations. So first of all, if we take into account identical particle combinations, then we are sensitive to quantum statistical effects. And now, depending on whether we deal with pairs of fermions or bosons, which obey Fermi-Dirac statistics or Bose-Einstein statistics. Here, for example, like for proton-proton case, due to anti-symmetrization of the wave function, quantum statistical effects are visible by these red dots. And for momentum difference approaching zero, the correlation function that arises due to quantum statistical effects approaches half. Then we are sensitive to final state interactions, and in case of charged particles, we have Coulomb interaction. For particles with same charges, we have repulsion. For particle opposite charges, of course, we have attraction. In case of two protons, we have Coulomb repulsion. And also in the case of two protons, very important and dominant is strong interaction. And you may see very typical characteristic shape of correlation function, which includes all effects and interactions mentioned before. In the case of non-identical particles, we are sensitive just to final state interactions, Coulomb for strong, Coulomb for charge, and strong for baryons, for example. Here you may see very nice example of proton-antiproton correlation functions, and this row here in this blue correlation function is related to annihilation processes between particles and antiparticles. Now I would like to say a few words about STAR experiment. It's currently only one experiment that is conducted at Relativistic Heavy Ion Collider at Brookhaven National Laboratory. STAR is abbreviation which stands for Solenoidal Tracker Trick. STAR is, as we know, a multi-purpose detector. It consists of many sub-detecting devices. In correlation femtoscopy, two sub-detectors are the most important for us. This is a time projection chamber and time flight detectors. So now let me move to results. I would like to start with interactions. So let me start that so far the knowledge of nuclear forces has been derived from studies that were made on nuclear and or nuclei. So the point is that nuclear forces between antinucleons was never studied before. And it's important to understand that knowledge of interaction between the most elementary example of antimatter, like antiproton is. So this knowledge is about interaction is simply, literally speaking, fundamental to understand properties of much more sophisticated systems. And here you may see results. So the task of these studies was to determine parameters of strong interaction in the case of antiproton system. So we have performed very detailed studies taking into account identical combinations of protons and antiprotons. And with very detailed comparison, having known parameters of strong interaction for proton-proton, we wanted to verify hypothesis whether strong interaction between two antiprotons can be described in similar way. And detailed studies of this analysis leads to the conclusion that yes, strong interactions parameters can be described in very similar way in the case of p-bar, like in the case of PP system. Here you may see the presentation of the most important strong parameters. F0 and D0. F0 is scattering length, D0 is effective range of strong interaction. So the point is that F0 and D0 for p-bar interaction is consistent with parameters extracted for proton-proton. So we have reached description of interaction between antimatter based on antiprotons, which are the most elementary examples of antimatter, which leads to the conclusion that we reached quantitative verification of matter-antimatter symmetry in context of forces that are responsible for the binding of antinuclei. Here you may see another set of results, including strange particles. Here is a proton lambda system. I would like to remind you that in the case of proton lambda, we are sensitive. We measure just strong interaction only. So we have checked all possible combinations of protons, antiprotons, lambdas, and anti-lambdas, and we group them into two categories like proton lambda, anti-lambda, and another combination particle and antiparticle. What we did, we extracted parameters of strong interaction for these cases. However, it's important to mention that in the case of these two groups of system, we reached different source sizes. We didn't expect it to measure different source sizes because we expect source size emitting pairs of protons and lambdas should have the similar sizes. However, in the case of particle-antiparticle combinations, we measured source size of half smaller than in the case of particle-particle case. And in order to understand why we see this difference, it's important to mention that these studies does not include residual correlation, feed-down correlations. So here we performed another studies. So we took into account in details contributions of residual correlations. I would like to mention this very important because, for example, in case of protons, very often in the experiment, we are not sure whether we deal with primordial proton or proton coming from, for example, weak decay of lambda, for example, particle. So the point is that we have very strong contribution of residual correlations coming from weak decays. And it's very important to extract this contribution. And the point is that after this detailed studies, we reached agreement between proton lambda and anti-proton lambda sources comparable to free femtometers. So it also shows that that inclusion of residual correlations is very important in the studies. Another set of results discuss lambda-lambda correlations. In lambda-lambda case, we are sensitive to strong interaction, but also to the quantum statistical effects. You may see experimental results of combinations lambda-lambda and anti-lambda. We took into account impact of residual correlations. We extracted parameters of strong interaction. The main motivation to this study was to verify whether we do or not see a lambda-lambda bound state, which is H-day baryon state. And from these studies with our data sample, we stated that we can't confirm existence of bound lambda-lambda state. Another set of results include omega particle. This is proton omega correlation system. So we wanted to determine binding energy, scattering length, effective range. We took into account 3 different parameterization of strong interaction. However, due to very pure statistics, when we compared the measured correlation function with theoretical predictions, taking into account that we determine scattering length as positive, it means that we favor proton omega bound state hypothesis. Now let me move to the second part of my presentation, which includes results from beam energy scan program. I would like to remind you that the STAR experiment is able to measure very wide area of QCD phase diagram with top peak energies. We are able to study these areas describing crossover transition between hadron gas and quark gluon plasma. So we study properties of system with high temperatures and low baryon chemical potential. And with beam energy scan program, when we go down with collision energy, we can scan another part of the QCD phase diagram. And the main goals of this program was to find the energy where we cannot see a transition from hadron gas to gluon plasma state. Another motivation was to find signatures and to study properties of first order phase transition between hadron gas and quark gluon plasma. Another very important motivation is to find the hypothetical critical point, which is between crossover and first order phase transition. That, of course, we're interested in some measurement related to chiral symmetry restoration. It's important to mention, to stress that this program realized in collider mode is also accomplished, is also determined with fixed target program. So with fixed target program, we are able to determine this area of QCD phase diagram, which reach baryon chemical potential up to 720 mH. Here you may see traditional HBT results of analysis for identical pions. So you have R out, R side, and R long source sizes. As I said, these are traditional HPT results for azimutally integrated analysis. I would like to remind you that with our site parameter, we are able to probe spatial source evolution in the transverse direction. Out component is a similar component, however, it also includes the time information. With R-long, we can measure source evolution in longitudinal direction. And the combinations of out and side are sensitive to, for example, emission time. We are also able to measure signatures of phase transition. And with R-long, we can probe source lifetime or temperature of kinetic freeze-out. And it's important to stress that with these results coming from the energy scan program complemented with tocric energies, we plotted final eccentricity as a function of initial eccentricity, which allows us to determine how system evolves. The conclusion is that system evolves faster in the reaction plane than in the direction perpendicular to this. And the point is that from these studies, we see that pion femtoscopy is not able to probe first order phase transition between hadron gas and gluon plasma. Here I would like to move to another particle species. We have combinations of pions, kaons, and protons. You may see very nice correlation functions for pion-kaon and proton-antiproton system. We are interested in this observables as a function of collision centrality, and you may see very clear centrality dependence. If we take into account different collision energies, we also see that we perform the studies for combinations of protons, antiprotons, and for example, pion-kaon, and we do see very clear dependence as a function of collision energy. Here you may see very interesting results of non-identical particle combinations taking into account all possible combinations of pions, kaons, and protons. And I would like to pay your attention to this interesting system of kaon-proton, because in the case of same charges, like in the case of K+ proton or K- antiproton, in this system, the correlation is determined mostly by Coulomb interactions. However, if we move to the system of opposite charges like K+ antiproton or K- proton, we see that very important is contribution of strong interaction. And the point is that having extracted source size for K+ or proton or K- antiproton, we can also determine parameters of strong interaction in the case of K+ antiproton, for example. I would like to move to the last aspect of my presentation. This is what we can learn from non-identical particle combinations. This is related to so-called asymmetry in emission process between non-identical particles. I would like to start that in terms of asymmetry, we distinguish between time asymmetry, space asymmetry, but also very often is that we simply don't know whether we measure space, time, or mixture of these asymmetries. So the point is that with non-identical particle combinations, taking into account spherical harmonic representation of this function, we can probe possible asymmetry in emission process. And first, the conclusion is that we do see a clear signal of asymmetry as a function of collision centrality and also for different collision energies, which means asymmetry does not disappear in lower energies and also in central peripheral data. And here you see a comparison of all these systems together, kaons, and protons. And there is very consistent conclusion from all these systems that heavier particles in average are emitted earlier because before lighter particles, or also the another scenario is that heavier particles are directed more towards edge of the system. To explain this, I would like to stress that particle velocity it consists of two components. The first one is flow, so-called radial component. The second is thermal, and the flow component is similar for both particle species. However, thermal component is different because it is inversely proportional to the mass of the particle, which means thermal component is smaller for heavier particles, and this smaller contribution if we take into account this formula describing a mean difference between mean emission points of two different particles types, we see that this smaller thermal component leads to bigger difference between emission points. And this brings me to my summary. So let me stress that I discussed three aspects. The first one, interaction, when we stress what are parameters of strong interaction for antiprotons as examples of antimatter. We also determine parameters of strong interaction for strange particles like lambda and omegas. And then we discuss geometrical properties. So from traditional HBT analysis, we discuss outside long components of source size. And also with this, we could extract information related to source lifetimes, particle duration, temperature of kinetic freeze-out, for example. And in terms of dynamics, the last aspect of my presentation was related to so-called emission asymmetries. So we were able to distinguish emission sequence to determine particle of which type is emitted earlier or later. And also we see a collectivity in this homogeneity region probed by non-identical particle combinations. Thank you very much for your attention.
Thank you, Hania. Okay, so we are open for discussion. Please raise your hand or use Mattermost channel. Don't see it for now. So maybe a quick question from my side. So you were saying about beam energy scan 2 program for STAR to go to lower energies, but also at the slide when you showed this different colliding species of STAR, there were also mentioned collisions of isobars. So I was wondering if there's a plan of doing the femtoscopy analysis for the isobar case as well?
Not at this moment. Not in terms of femtoscopy. Okay. I don't know anything about this.
Okay, thank you. So let's wait for a bit. Yeah, there's a hand, Yuri.
Thank you. So, well, you've reported a lot of results, so thanks for talk. I actually have a question. So around slide 19, you made a statement that probably the femtoscopy, the traditional femtoscopy, wouldn't resolve the difference between the first order phase transition and the crossover transition in the equation of state. At least so I understood. So I just wanted to comment that in principle we made a study with Dubna, with colleagues from Dubna in the hybrid viscous hydro plus cascade model with 2 different equations of state. And there are some caveats in the study, but in principle, what we saw at the end is that for the lowest collision energies, at the time it was 7.711 GeV, it seems that the EOS with the first order phase transition is slightly more preferable than the crossover one. So it's a kind of slight hint. There are caveats, but still we kind of saw something in the analysis.
Yes, thank you very much for this comment. And I would like to also stress and maybe add also as a comment that here I presented results of identical of pions, but there is also a plan to measure if statistics allows, because this is what we expect with second phase of beam energy scan program, we would like to focus on azimutally sensitive interferometry, femtoscopy method for protons. And we hope it will also help to improve what we know about transition.
Okay, thank you. I'm looking if there are more hands. If not, thanks you again for a really nice overview of STAR results. And we will move to the next talk.
Thank you.
Okay, so the next talk is by Krzysztof Woźniak. Krzysztof, yes, I can see you. So Krzysztof will talk about the recent ATLAS measurements on correlations in lead-lead and xenon-xenon collisions. I can see your slides, so you can start.
Okay, so first I would like to thank the organizers for a chance to present these results. As you can see, the cover photo is selected not by purpose. It represents the main phenomenon which I will be talking about, the flow. Okay, so as an introduction, we know that in the collisions of nuclei, the quark-gluon plasma is created, and there are two main phenomena connected with it. So particle flow, which is related to the geometry of the collision, initial geometry of the collision, which usually is not symmetric, and this causes that gradients of pressure lead to some azimuthal correlation in the events. This is the subject of my talk and of the talk earlier today by Adam Trzupek. There are also strong interaction in quark-gluon plasma where the partons created in the collision lose the energy in the matter, but this was the subject of the talk by Helena Santos on Tuesday. Going to the first measurement, I would like to show the most detailed analysis of the lead-lead collisions at 5 TeV. So in this case, a detailed measurement of harmonics from V2 up to V7 was performed. We can see results of values of harmonics as a function of PT for different centrality intervals, starting from most central events in the upper left corner and going down and to the right to the most peripheral analyzed by ATLAS. In all cases, we can see that as a function of PT, harmonics increase up to 3 GeV, and then a small decrease is observed. The centrality dependence is that we have smallest values in the most central collisions, and they grow in mid-central and then again decrease in the most peripheral collisions. Similar measurement was more recently done for the xenon-xenon collisions. Here we had only one run available, so we have measured statistically significant harmonics from V2 to V6. And at the first look, you can see that the shape of the PT dependence is similar to that of lead-lead collisions. However, if we compare them more precisely, as it is done here, we can see that there are some differences. So first of all, the elliptic flow in the most central xenon-xenon collisions is much higher than in lead-lead collisions. Then it fast decreases and it becomes smaller than in lead-lead collisions. Similar trend, but less strong, is for other harmonics like V3 and V4. For V4, V5, we can see that the values of xenon-xenon flow are slightly smaller than in lead-lead collisions, but not that much. In the xenon-xenon collision, we have also analyzed the scaling of harmonics of different orders, dividing the harmonics by elliptic flow to the power related to the order of the harmonics. And after such scaling, we can see that the harmonics are not dependent on PT anymore. We can even fit a constant value for different harmonics scaled for all centralities. These fits are represented by dashed lines. The similar scaling using the triangular flow here gives even more interesting results. It is not only constant as a function of PT, but also very similar values are obtained for all orders of harmonics. And at the first look, also for different centralities. To investigate this more precisely. We have done the comparison of values of scaled harmonics as a function of centrality. Here are those scaled by elliptic flow, and here by triangular flow. So for elliptic flow, as it was earlier seen, there is a strong centrality dependence, so the highest values, scaled values, are in the most central collisions, and especially in the highest harmonics, and they decrease fast and become much smaller in peripheral collisions. For the scaled values using triangular flow, one can argue that there is a single scale value for which all harmonics at all centralities are compatible. It is something like 1.4. This observation can be concluded that after measuring V3, we may predict the PT and centrality dependence of all other higher harmonics. This may be related to the fact that the harmonics from V3 are not related so much to the average shape of the collision region, but to the fluctuation of this region. Okay, the harmonics, flow harmonics may be dependent not only on the transverse momentum and centrality, but also may change with the pseudo-rapidity of the particles. And here we can expect two types of changes, fluctuations. One which is related to the absolute value of the harmonics, and the other which is related to the change of the event plane or twist of the event plane for the harmonics. This type of harmonics fluctuation can be studied using correlators calculated from flow vectors in different pseudo-rapidity intervals. There are two correlators, small r and capital R, and both of them, in the absence of any systematic modification of flow harmonics, should be equal 1. These correlators are measured in lead-lead and xenon-xenon collision. So first, I show results for lead-lead collisions. We can see here correlator small r as a function of distance in pseudo-rapidity for different orders of the correlator and different ranges in the centrality. In all cases, this dependence on pseudo-rapidity is approximately linear. For the elliptic GDER correlator, we can see that it decreases to something a bit lower than 0.95 in the most central and in the peripheral collisions, but only to about 0.97 in the mid-centrality. The other higher order correlators decrease more because they drop even below 0.9, and we do not see an evident dependence on centrality here. Also, if we compare the values obtained for two energies of lead-lead collisions, 2.76 and 5.02, we do not see big differences. The correlator capital R has very similar properties. It also decreases approximately linearly. It also reaches about 0.95 for the elliptic correlator and about 0.9 or even less for higher order correlator. The centrality dependence, if there is for the elliptic, the correlator is less significant. And again, there is no difference for two collision energies. Now I change results to those for xenon-xenon collisions. We also observe linear dependence, and here we can see that the R22 correlator is much larger than the higher order correlators, because more clearly because they are on the same plots. The fact that everything seems to be linear in the pseudo-rapidity allows us to approximate it by the function linear, with the slope parameter related to the correlation strength parameter. It can be defined by the fit or calculated using the formulas presented here. We can see that the elliptic decorrelator correlation strength parameter is quite high at the most peripheral collisions, represented by low values of number of participants, and decreases for mid-centralities and increases again for the most central collisions, but not that much as for peripheral collisions. Looking at the other higher order strengths, the correlation parameters, we cannot see that clear centrality dependence. Maybe for F4 it is still present, but the centrality is not, dependence is not obvious. When we compare these parameters from lead-lead collisions to those found in the xenon-xenon collision, we can see that the F2 parameter is larger in xenon-xenon collisions, but it is of the same order, maybe slightly lower in the case of F3 in the higher order parameters. Okay, and now I was talking at first about the magnitude and flow decorrelation and twist decorrelations. So they are directly related with the strength parameters shown earlier. The correlation connected with twist is just equal F for the capital R decorrelator, and the asymmetry or magnitude fluctuation is the difference between small r and capital R F parameters. We can see that the twist and asymmetry the parameters are very similar, both for 2-2 and 3-3 order. Maybe there is some difference for the third order. The other thing is that the third order fluctuations are higher than those of the first order. Okay, so in the ATLAS experiment, we have also measured fluctuation of anisotropic flow on event-by-event basis, calculating the probability function of Vn values, or two-dimensional correlation of different orders, using, in this case, multi-particle cumulants calculated for different centralities and PT ranges. Here are a list of some most important observations. So the negative C14 leading to positive V14 harmonics shown in the upper plots was found. There's also negative C44, which implicates that there are nonlinear contribution to V4, which are proportional to V2 squared. The asymmetric cumulants NSC23 are negative, which reflects the anti-correlation between V2 and V3. Because of the positive NSC24, we can say that it confirms nonlinear contribution to D4, to V4. And one important remark has to be made, that in the analysis like this, it is necessary to account for centrality fluctuation, which lead to additional Vn fluctuation as well. And this has to be taken into account in the analysis. And the last subject in my talk is the flow of charm and bottom hadrons. In the ATLAS experiment, we use reconstructed muons from charm and bottom hadron decays, separating them from muons from pi or chi background, using the imbalance between momentum measured in the inner detector, in the closest to the interaction point, and measured in the muon spectrometer. And also the transverse impact parameter of these muons has different distributions for different types of origin of the muons. So using this separation, we can calculate the elliptic flow for bottom and charm muons, and this for bottom muons is much smaller than for charm muons, as we can see in the plots, for all centralities, and practically for all PT values, maybe in the highest values there is some doubt about it. Also V3 was measured, and in this case again that for triangular flow for bottom muons is much smaller. It is even close to 0, so it's much smaller. And this type of measurements are useful to differentiate between different models of QGP expansion, as it is shown here. Such comparison was shown in the paper listed at the bottom. So in conclusion, I would like to say that detailed analysis of azimuthal correlation was performed in lead-lead and xenon-xenon collisions. The scaling of harmonics of different orders was investigated. Fluctuation of harmonics as a function of pseudo-rapidity were measured. Also analysis of event-by-event fluctuations with multi-particle cumulants was performed, and flow of charm bottom hadrons was measured. All these results allow deeper insight in the properties and expansion of quark-gluon plasma and the effects of fluctuation of initial condition in the collisions. And that's all. Thank you.
Thank you for very nice talks. So we have quite some time for questions now. So please, yeah, I see you. Jörg, go ahead.
Hi. So very nice talks, thanks. So I have a question on slide 8, where you show this very interesting scanning picture. I'm not sure what's the physics mechanism behind this normalization or scanning, but I was wondering if you can get a better scanning using the nonlinear flow mode of this higher harmonic. Let's say V5 coming from V3, V2. So, and then you use V532 for the scanning. And similarly for V6, you instead of using the total V6, you can use the V6 to study such a scanning, because then you can really remove the linear contribution from epsilon 6, and then you can suppress the contamination in a central collision. I guess it will get a better scanning in the end.
So this type of studies were not performed. I think that it depends on if we can return to this type of analysis. So then we may try it.
Because Atlas did this event by event fit before using the event shape engineering, and I guess.
This I don't think that this was tried yet.
Okay, thanks.
Okay, I see Boris. Boris, please.
Yes, thank you. I have a question to the same point, and so maybe it's not only for the speaker, but maybe for you as well. I don't know. How is, because I'm trying to understand what does it mean if, say, V4 scales with V3 to the 4/3, if this is like not a whole number in the exponent. Now, how would this scaling be related to the non-symmetric cumulants where I mean, different orders of the V's are mixed? Is there a relation, or is this a completely different thing? Okay, I wonder maybe that was.
I'm not sure if this question is to me, but
okay, yeah, I see.
Yeah, if the speaker will not answer, I may say a few words, because I mean, this scanning is something we tried in different energies, right? I think there's a beautiful paper from Roy Lacey to test such a scanning. And for me, for higher harmonic, I don't see any physical reason to have this scanning. However, if you only look at nonlinear component, which coming from lower order eccentricity, then it might be quite interesting to do the scanning for V6 222 and do the scanning of V2 to the power 6 divided by 2. And whether it's connected to symmetric cumulants, I don't think so, because one is you study the linear correlation, and the other you study the event by event fluctuation of the correlation. So they are different physics, I believe.
Mm-hmm. Okay, thanks.
Thank you. I don't see more hands now. Maybe I have one question related to this charm and bottom V2 and V3 that you showed. So you showed results on V2 and you compared them to models, but now you also for V3 you have some ordering, let's say, of V3 of charm and bottom muons. So I was wondering if you have a comparison to model for V3 as well.
No, there was no comparison, I think, in the paper.
Okay, thank you.
But I would have to check.
Yeah, I was yeah, that would be also probably interesting to see for the completeness, because the models describe quite nicely V2. Would be just interesting to see. Okay, thanks. I'll check still the Mattermost. There's nothing. So thanks again, Krzysztof, for the talk. And we are going to move to the last. Yeah, please stop sharing. So the last but not least talk is by Vytautas Vislavicius. Vytautas?
Yeah, hi.
Yes, I can see you. Let's wait for the... Yeah. Okay, now you can. So the talk will be on constraining the transport properties of quark-gluon plasma with the latest flow measurement in ALICE. Please start.
Yeah, and you see the slides, right?
Yes, everything is
good. Fine. Yeah, okay. So I would like to start with saying thanks to the organizers for giving this opportunity to talk. As Barbara already mentioned, the title, Constraining the Transport Properties of the Quark-gluon Plasma with the latest flow measurements from the ALICE. So usually when we talk about the heavy ion collisions, we consider these extended spatial objects represented by the blue balls here that contains of nucleons. And then of course, if the collision is not heads-on, then we have this overlapping region denoted by this orange blob where we create the quark-gluon plasma. Now, of course, the nucleons in this region, they will exhibit some spatial anisotropies, which will give rise to different pressure gradients. So the pressure gradients in X direction will be larger than pressure gradients in Y direction. And so the quark-gluon plasma, it will expand more rapidly in X direction as compared to the Y direction. And now if we produce particles there, then particles produced in X direction will receive an additional kick. And so this we call particle flow. Now, of course, in real life, the shape is not a perfect ellipse. It's never a perfect ellipse. And so if we consider a collision in the transverse plane, so here in purple circles, we have the colliding nucleons. We see that the geometrical shape is quite complex. What we can do, we can expand this using Fourier series. So we get a superposition of different shapes. So we get one that looks like an ellipse. So that is the it comes with a weight v2 that we usually call then the elliptic flow coefficient. Then we also have v3, this blue lines here, which corresponds to the triangular flow, also the quadrangular flow v4, and so on and so on. So these flow coefficients, in principle, they are they can be calculated as the average of cosine of where the argument of the cosine is the angle of the particles minus the event plane of the corresponding harmonic. And nowadays we have more sophisticated methods to calculate this. So in this talk, I will consider the results calculated using the M-particle correlations. So in principle, when I say for instance, V2-4, I mean the V2 calculated with 4-particle correlation and so on. And okay, so as I said, so we have this collision, which has the, we have the collision geometry, then we also have fluctuations and so on. And then all this is transported, the system then evolves, and it turns out that this evolution is very similar to that of a fluid. So it follows the hydrodynamical laws, and therefore it makes sense to talk about the properties of this fluid. So shear viscosity, bulk viscosity, and so on. So on the plot on the right, I'm showing nice results from Alice from 2016. So here we have different flow harmonics, V2, V3, V4, calculated with different order of particle correlations. And we have the results from 5 TV lead in solid markers, and then 2.76 TV in hollow markers. And then another notation here where I write delta eta larger than 1. So here we basically, when we correlate two particles, we impose an eta gap between them in order to suppress short-range correlations that might originate from, for instance, from jets and so on. So yeah, we call them non-flow. And then in addition, on this plot, I also have the predictions from the hydrodynamics, as you can see. And we see that the hydrodynamical models, they predict the data quite well here. Now, of course, we can, if we want to say something more about these parameters, eta over s, zeta over s, we can go into the model and fiddle with the parameters there. Or alternatively, we can use a more sophisticated method. So there's a very nice paper published in Nature Physics last year, where a global Bayesian fit is done. So we take a large set of input data that also contains particle yields and mean PT and so on. And then we fit everything together with a number of, the fit contains a large number of different parameters, but from that we are able to extract the shear viscosity and the bulk viscosity as a function of temperature. So now, as you see here, these parameters, these results, they still have quite large credibility regions, and of course, to reduce those, we also need to provide more results that could be included in this Bayesian fit. So as I said before, we have the initial geometry that fluctuates, and then we have the evolution of the system. And so all these fluctuations of the initial geometry, they will be also translated into the fluctuations of V2. And therefore, it makes sense to talk about the probability density function of any of the flow coefficients. So on the plot here, I'm showing the PDF of V2 in black bands here. This is for lead-lead 5TV collisions and 35 to 40% centrality. And then on top of that, I think what is interesting to see, we have the predictions from different hydrodynamical models. So we have different models for initial conditions, and then we also have music and then by event vision and so on. And we see that once we consider initial state, well, different initial state models, and then the hydrodynamical evolution, we can also describe this underlying PDF of V2 quite well. So before I move to the results, I just want to have a few words on the Alice detector that made all these results possible. But since it's not the first talk on Alice today, I will just mention that for the results that I will show today, we mostly consider the inner tracking system and the time projection chamber, which is used for both tracking and particle identification, and then also the V0 detector, which is used for multiplicity estimation at forward pseudo rapidities. And the results that I will be showing today, they will be obtained from lead-lead collisions at 5 TeV. So currently we have already a large set of flow measurements in Alice coming up. So what I'm showing here are the PT differential V2s now measured with different orders of particle correlation. So we have V2, V24, V26, and V28. And this is now only in one centrality class. We have 40 to 50%, but of course we have the other centrality classes as well. And on the plot on the left, I show V24, 6, and 8 without eta gap. And on the right, we have eta gap larger than 0. And I think this is already an interesting result. If we consider the V24, 6, and 8 with and without eta gap, we see that this the changes are quite small. So we can already say that V2 calculated with the 4, 6, and 8 particle correlations are not so sensitive to the non-flow effects. Now, on the other hand, if we compare, for instance, V24 with the V22, even when we use a large eta gap for V22, we still see a large difference between the two. And this is then mostly attributed to flow fluctuations, which principally proves the second moment of the V2 PDF. And before we talk about the flow fluctuations, let's consider higher moments of the PDF for a moment. So historically, we've been saying that the PDF of V2 is given by the most simple case Bessel Gaussian distribution, which would then imply that the second order of the PDF, the second moment of the PDF, and all higher moments are the same, which would in turn imply that V24 should be the same as V26 and V28 and so on. Now, this is something that we can measure with the data we have already available. So the two plots that I'm showing here are V26 over V24 and V28 over V24 ratios. And on the left, we have 5 to 10% centrality, on the right, 30 to 40. And we see that below 3.5 GV, these ratios are not at unity. They're deviating by around 1% from the unity, which one could say it's not a large deviation, but this is also consider, for instance, 30 to 40%, we see that the significance of this deviation is quite large. So we can take one step further and calculate explicitly the skewness and kurtosis of these distributions. So this is the skewness, gamma 1, denoted in red points, and the kurtosis, gamma 2, denoted in blue points, again for two centrality intervals. And we find that, again, below 3.5 GV, the skewness is negative. It's around 0.3 value or so, which is, I think it's an interesting result because 0.3, well, this minus 0.3 is also a result that we get from hydrodynamical models when we consider the PT integrated PDFs. And then also the kurtosis gamma 2 and semicentral collisions, we see that it's positive. So we also have tails that are somewhat fatter than what we would expect for a normal Bessel Gaussian distribution. So I think like what is interesting to see here is that we see that the PDF actually evolves with the transverse momentum. I think this would be an interesting test for hydrodynamical models. Then I already showed the PT integrated PDF of V2 a few slides earlier. But another interesting thing that we can do is, well, we said that this PDF, it's, well, I mean, it depends, first of all, on the collision geometry, which is controlled by the centrality. And then on top of that, we also have the fluctuations in the initial state. What we can do further is we can use the event shape engineering techniques, which is a popular technique in flow measurements, which allows us to select large flow vector or small flow vector. So basically bias ourselves to large V2 values or to small V2 values. So if we select the large flow vector denoted by this Q2 here, we of course see that we are selecting a larger V2 than as in without the event shape engineering. I think an interesting thing to see is that once we do that, so we also kind of selecting a PDF that is more skewed than in the general case where we don't apply the event shape engineering techniques. And this is, I think, is an interesting result for initial state modeling. Then before we move to the flow fluctuations, the first thing we need to do is measure the V2 with the 4-particle correlation, because that probes the second moment of the PDF. And in Alice, we can do that we can couple that with particle identification. So this is the Alice result for V24 for different hadron species. And so here in principle, we don't see anything unexpected at this point. We see that at low PT, there's a mass ordering, which is predicted by the hydrodynamics. And then also at higher PT, we have a grouping between baryons and mesons, which then would suggest some coalescence. But we can take this result and use that to calculate the flow fluctuations. So what I'm showing here on this plot now is the relative flow fluctuation. So sigma of V2 divided by the mean value. Again, for different hadron species. And I think this is a very interesting result. If we consider the data points, we see that all these particles follow the same trend. So in principle, there is no obvious species dependence. So basically all light-flavored hadrons, they fluctuate the same way. And on top of that, we can also put predictions from hydrodynamical models. So here we only have pions, kaons, and protons. We use AMPT initial conditions and then apply event by event Vishnu. And if we consider the model predictions, we see that, well, first of all, at low PT, the model predicts quite large splitting of the FV2, but there's also seems to be a splitting of FV2 at larger PT as well. Now, of course, here the bands are quite wide, and to say something more how significant this is, the model bands should be reduced. So if we want to say whether the splitting is significant or not. So we talked about the V2 fluctuations, then I think it's also interesting to talk about the flow vector fluctuations. And to study that, we construct this factorization ratio, Rn. So basically, we take two particles from different PT regions and then divide them by flow vectors calculated in the same PT regions. And so if this Rn is below unity, that means that the factorization is broken and therefore the flow vector fluctuates. And if we calculate that, so these are the results that we get. So we have 0 to 5% on top left, and then 40 to 50% centrality at bottom right. We see that indeed, as the gap between PTA and PTT increases, this factorization is broken. So as we increase the gap in transverse momentum, and this is more pronounced in more central collisions. And I think it's also nice to see that the hydrodynamics, so we have two hydrodynamical predictions using two different initial state models. We have Trento and AMPT. And we see that these trends are at least qualitatively reproduced by the hydrodynamical models. So then we can, since this is a flow vector we're talking about, in principle it has a flow angle and it has a flow magnitude. So we can ask whether it's the angle or the magnitude that fluctuates. Now, of course, calculating the fluctuations of magnitude is a little bit less trivial. So I will only talk about the angle fluctuations. And to calculate those, we construct a ratio of 4-particle correlation given by this guy here, where again, phi A and phi B are particles from different PT regions. And so this observable is in principle only sensitive to the PT-dependent flow angle calculations. So if we consider then, again, here we have this ratio and 0 to 5% on top left, 40 to 50% as bottom right. And if we consider these ratios, we find that pretty much everywhere this ratio is consistent with unity, which then suggests that it's not the flow angle that drives the flow vector fluctuations, but instead it's the flow magnitude fluctuations. So that brings me to the summary. So in principle, by now we have quite a large number of precision flow measurements that provide a lot of input to continue the studies on the properties of the quark gluon plasma, as for instance, for studies such as like the global Bayesian fits. We talked about the probability density function of V2. We said that it's sensitive to the collision geometry, which is in turn important for initial state modeling. We also said that below 3.5 GeV in PT, the PDF is not described by the Bessel-Gaussian distribution, which would be an interesting test for hydrodynamical models. V2 fluctuations seem to be independent of particle species, and so far AMPT with Vishnu they predict the splitting of FV2. The flow vector factorization is broken with the increasing gap in transverse momentum, and this is also more pronounced for central collisions. And so it's nice to see that this can be described by hydrodynamics. And finally, we also said that the flow vector fluctuations, they indicate to be dominantly driven by the flow magnitude fluctuations as opposed to flow angle fluctuations. So that would be all from my side, and thanks a lot.
Thank you, Vytautas, for a very nice talk, and we have quite some time for questions or discussion. So please raise your hand if you have a question. I'm checking the chat. I don't see any so far. Yes, there's one from Boris.
Yeah, so I'm struggling with understanding, but maybe there is no simple understanding. But still, let me ask this question. So you've shown that you can measure the skewness and the kurtosis of the PDF of the I think V2, V3 was there. Is there an, I mean, of course, I understand I can run a model and get the same, well, get a skewness and kurtosis and compare that. But is there an idea, like, what does this tell to me? Like, okay, if the skewness is such and such, then the viscosity must be whatever, or then the initial condition must be something. So I don't know, maybe not, but I just wonder if you have an idea about this.
Yeah, so I mean, in principle, if we talk about the PDF of V2, right? I mean, so it's not exactly trivial to just measure these points. We have to measure different moments of that. And from that, we can unfold this full distribution. So for that, that's why we measure these skewness and kurtosis, and then ideally higher moments and so on, because more moments we know, the better control we have of this PDF. Now, why it's interesting to measure the PDF, it's a completely different story, because this is really what tells us about the initial conditions and also how the how it evolves from the initial conditions to the final observable, which is the V2, right?
Okay, I think I'm feeling the idea. Yeah, thanks.
Yuri?
Okay, so Boris, more precise answer to your question is that exactly on this slide, if you look at this probability distribution for the V2, the idea behind this, as far as I understand it, is that different eta over S or whatever transport you input to hydro, it basically shifts this overall shape to the right or to the left, but the shape itself is kind of driven by the initial state. So the shape of that, it can only be shifted by the hydro, but the shape itself is basically unique to the initial state model which you use.
Okay, thank you. You wanted to say something?
Yeah, answer the comment or because that's exactly why Ricardo's present the PD differential. Because if there's no PD dependence, then everything will be the same as initial condition. Then it's not. I mean, there's no need to do any PD differential. It's the same with kinematic cost, right? So for V2, PV2 distribution will be the same as P eccentricity distribution. Then you use the data to constrain the model. However, from this non-trivial PT dependence, it's clear that the transport properties will modify not only the magnitude of the V and or the shape of the P, I mean, or the shift left and right of the PV2 distribution, but also the shape. And it will be more skewed or more kurtosis distribution if you have a different Edelweiss. I guess that's the main point of this figure.
Thanks for the comment. Let me see. Nothing on the Mattermost, no questions. I just want to remind that if you still would like to discuss or have more questions, then the Mattermost channel will be open and all the discussion will be also archived, so it will not disappear even if you have still some questions later to any of the speakers. So thanks again, Teudas. And with this, we actually finish the heavy ion, the parallel heavy ion sessions of ICHEP. So I would like to thank again all the speakers from today and remind you that the ICHEP continues next week with plenary sessions starting on Monday. Okay, bye-bye.
Thanks, Barbara. Bye.
Bye-bye.